like it. When you look at the long-term vision of autonomous vehicles, do you see machine learning as fundamentally being able to solve most of the problems? So learning from experience.
I'd say we should be very clear about what machine learning is and is not. And I think there's a lot of confusion. What it is today is a technology that can go through large databases of repetitive patterns and find those patterns. So an example, we did a study at Stanford 2 years ago where we applied machine learning to detecting skin cancer in images. And we harvested or built a data set of 129,000 skin photo shots that all had been biopsied for what the actual situation was. And those included melanomas and carcinomas, also included rashes and other skin conditions, lesions. And then we had a network find those patterns, and it was by and large able to then detect skin cancer with an iPhone as accurately as the best board-certified Stanford-level dermatologist. We proved that. Now this thing was great in this one thing, I'm finding skin cancer, but it couldn't drive a car. So the difference to human intelligence is we do all these many, many things, and we can often learn from a very small data set of experiences, whereas machines still need very large data sets and things that be very repetitive. Now, that's still super impactful because almost everything we do is repetitive. So that's going to really transform human labor. But it's not this almighty general intelligence. We're really far away from a system that would exhibit general intelligence. To that end, I actually commiserate the naming a little bit because artificial intelligence, if you believe Hollywood, is immediately mixed into the idea of human suppression and machine superiority. I don't think that we're going to see this in my lifetime. I don't think human suppression is a good idea. I don't see it coming. I don't see the technology being there. What I see instead is a very pointed, focused pattern recognition technology that's able to extract patterns from large data sets. And in doing so, it can be super impactful, right? Super impactful. Let's take the impact of artificial intelligence on human work. We all know that it takes something like 10,000 hours to become an expert. If you want to be a doctor or a lawyer or even a really good driver, it takes a certain amount of time to become experts. Machines now are able and have been shown to observe people become experts and observe experts and then extract those rules from experts in some interesting way. They could go from law to sales to driving cars to diagnosing cancer, and then giving that capability to people who are completely new in their job. We now can, and that's been done. It's been done commercially in many, many instantiations. So that means we can use machine learning to make people expert on the very first day of their work. Like, think about the impact. If your doctor is still in their first 10,000 hours, you have a doctor who's not quite an expert yet. Who would not want a doctor who is the world's best expert? And now we can leverage machines to really eradicate the error in decision-making, error in lack of expertise for human doctors. That could save your life.
If we can link on that for a little build, what do you think it takes to build an intelligent system and an intelligent robot?
I think the biggest innovation that we've seen is machine learning. And it's the idea that their computers can basically teach themselves. Let's give an example. I'd say everybody pretty much knows how to walk. And we learn how to walk in the first year or two of our lives. Mm-hmm. But no scientist has ever been able to write down the rules of human gait. We don't understand it. We have it in our brains somehow. We can practice it. We understand it, but we can't articulate it. We can't pass it on by language. And that to me is kind of the deficiency of today's computer programming. When you program a computer, they're so insanely dumb that you have to give them rules for every contingencies. Very unlike the way people learn from data and experience, computers are being instructed. And because it's so hard to get this instruction set right, we pay software engineers $200,000 a year. Yeah. Now, the most recent innovation, which has been in the make for like 30, 40 years, is an idea that computers can find their own rules. So they can learn from falling down and getting up the same way children can learn from falling down and getting up. And that revolution has led to a capability that's completely unmatched. today's computers can watch experts do their jobs, whether you're a doctor or a lawyer, pick up the regularities, learn those rules, and then become as good as the best experts.
So the dream of in the 80s of expert systems, for example, had at its core the idea that humans could boil down their expertise on a sheet of paper. So to sort of reduce, sort of be able to explain to machines how to do something explicitly. So do you think, what's the use of human expertise into this whole picture? Do you think most of the intelligence will come from machines learning from experience without human expertise input?
So the question for me is much more, how do you express expertise?
Yes.
You can express expertise by writing a book. You can express expertise by showing someone what you're doing. You can express expertise by applying it by many different ways. And I think the expert systems was our best attempt in AI to capture expertise in rules, where someone sat down and say, here are the rules of human gait. Here's when you put your big toe forward and your heel backwards, and here how you stop stumbling. And as we now know, the set of rules, the set of language that we can command is incredibly limited. The majority of the human brain doesn't deal with language. It deals with like subconscious numerical perceptual things that we don't even self-aware of. Now, when a AI system watches an expert do their job and practice their job, it can pick up things that people can't even put into writing, into books or rules. And that's where the real power is. We now have AI systems that, for example, look over the shoulders of highly paid human doctors like dermatologists or radiologists, and they can somehow pick up those skills that no one can express in words.
You'll probably disagree about this question, but what is your biggest, would you say, disagreement about either something profound and very important or something completely not important at all?
I don't think we have any disagreements at all.
I'm not sure that's true.
We walked into that one, didn't we?
Yeah,
so
that's pretty good.
one thing that you sometimes mention is that, and we did this one on air too, as it were, whether or not machine learning is computational statistics.
It's not.
But it is.
Well, it's not. And in particular, and more importantly, it is not just computational statistics.
So what's missing in the picture? What's
All the rest of it.
What's missing? That which is missing. Oh,
Well, because
yes. Well, you can't be wrong now.
Well, it's not just the statistics. He doesn't even believe this. We've had this conversation before. If it were just the statistics, then we would be happy with where we are. But it's not just the statistics.
That's why it's computational statistics.
Or if it were just the computation.
I agree that machine learning is not just statistics.
It is not just the statistics.
We can agree on that.
Nor is it just computational statistics.
It's computational statistics.
It is computational.
What is
It's
the
not just statistics.
computational and computational statistics? Does this take us into the realm of computing?
It does, but I think perhaps the way I can get him to admit that he's wrong, is that it's about rules.
It's about rules.
It's about symbols. It's about all these other things.
But statistics is not about rules? I'm going to say statistics is about rules.
But it's not just the statistics, right? It's not just a random variable that you choose and you have a probability
I think you have a narrow view of statistics.
Okay, well then what would be the broad view of statistics that would still allow it to be statistics and not say history that would make computational statistics okay?
Well, okay, so I had my first sort of research mentor, a guy named Tom Landauer, taught me to do some statistics, right?
Sure.
And I was annoyed all the time because the statistics would say that what I was doing was not statistically significant. Mm-hmm. And I was like, but, and basically what he said to me is, statistics is how you're going to keep from lying to yourself, which I thought was really deep.
It is a way to keep yourself honest in a particular way. I agree with that.
Yeah, and so you're trying to find rules. I'm just kind of bringing it back to rules.
Wait. Could you possibly try to define rules?
Even regular statisticians, non-computational statisticians, do spend some of their time evaluating rules, right? Applying statistics to try to understand, does this rule capture this? Does this not capture that?
You mean like hypothesis testing kind of
Sure.
thing? Or like confidence intervals? I think
more like hypothesis. Like I feel like the word statistic literally means like a summary, like a number that summarizes other numbers.
Right.
But I think the field of statistics actually applies that idea to things like rules, to understand whether or not a rule is valid.
So software engineering statistics?
No.
Programming languages statistics?
No.
Because I think it's useful to think about a lot of what AI and machine learning is, or certainly should be, as software engineering, as programming languages. To put it in language that you might understand, the hyperparameters beyond the problem
See,
itself.
hyperparameters has too many syllables for me to understand.
The hyperparameters of
That's better.
that goes around it, right? It's the decisions you choose to make. It's the metrics you choose to use. It's the loss
So
function.
you want to say
choose
the
focus on.
practice of machine learning is different than the practice of statistics. Like the things you have to worry about and how you worry about them are different. Therefore, they're different.
Right. At a very little. I mean, at the very least, it's that much is true. It doesn't mean that statistics, computational or otherwise, aren't important. I think they are. I mean, I do a lot of that, for example. But I think it goes beyond that. I think that we could think about game theory in terms of statistics, but I don't think it's very as useful to do. I mean, the way I would think about it, or a way I would think about it, is this way. Chemistry is just physics. But I don't think it's as useful to think about chemistry as being just physics. It's useful to think about it as chemistry. The level of abstraction really matters here.
So I think it is. There are contexts in which it is useful.
Yes.
Think of it that way, right?
No,
and
that
so
is
finding that connection is actually helpful. And I think that's when I emphasize the computational statistics thing. I think I want to befriend statistics and not absorb them.
Here's the a way to think about it beyond what I just said, right? So what would you say, and I want you to think back to a conversation we had a very long time.
And when they were starting their online master's program, he knew that I was really excited about MOOCs and online teaching. And he's like, I have a plan. And I'm like, tell me your plan. He's like, I can't tell you the plan yet, because they were deep in negotiations between Georgia Tech and Udacity to make this happen. And they didn't want it to leak. So Charles would kept teasing me about it, but wouldn't tell me what was actually going on. And eventually it was announced, and he said, I would like you to teach the machine learning course with me. I'm like, that can't possibly work. But it was a great idea, and it was super fun. It was a lot of work to put together, but it was really great. And
Was that the first time you thought about? First of all, was it the first time you got seriously into teaching?
I mean,
I'm
I
trying
was
to get
a professor.
the timing right. Oh, so this was already
And I had
already
done-
after you jumped to. So like,
Yeah.
there's a little bit of jumping around in time.
Yeah, sorry about
There's
that.
a pretty big jump in time.
So like the MOOCs thing.
So Charles got to Georgia Tech, and maybe this is a
I got
Charles
this
story.
in 2002.
He got to Georgia Tech in 2002, and but then and worked on things like revamping the curriculum, the undergraduate curriculum, so that it had some kind of semblance of modular structure, because computer science was at the time moving from a fairly narrow, specific set of topics to touching a lot of other parts of intellectual life, and the curriculum was supposed to reflect that. And so Charles played a big role in kind of redesigning that. And then
and for my labors, I ended up the associate dean.
right, he got
somehow.
to become associate dean in charge of educational stuff.
Well, I was
This should be a
undergraduate.
valuable lesson. If you're good at something, they will give you responsibility to do more of that thing
Well,
until you
Don't show competence.
Don't show competence if you.
Well, you know
don't
what they
want
say.
responsibility.
here's what they say.
Yeah.
The reward for good work is more work.
Yeah.
The reward for bad work is less work. Which, I don't know, depending upon what you're trying to do that week, one of those is better than the other.
Well,
But
one of the problems with the word work, sorry to interrupt, is
Sure.
that it seems to be an antonym in this particular language. We have the opposite of happiness, but it seems like they're like that's one of, we talked about balance. It's always like work-life balance. It always rubbed me the wrong way as a terminology. I know it's just words.
Right, the opposite of work is play, but
Yeah.
ideally work is play.
Oh, I can't tell you how much time I'd spend, certainly when I was at Bell Labs, except for a few very key moments. As a professor, I would do this too. I would just think, I cannot believe they're paying me to do this. Because it's fun. It's something that I would do for a hobby if I could anyway. So that sort of worked out.
You sure you want to be saying that when this is being recorded?
As a dean, that is not true at all. I need a raise. But I think here with this, that even though a lot of time passed, Michael and I talked we texted almost every day during the period.
Charles at one point took me, there was the ICML conference, the machine learning conference was in Atlanta. I was the general chair of the conference. Charles was my publicity chair or something like that, or fundraising chair.
Fundraising chair.
Yeah. But he decided it'd be really funny if he didn't actually show up for the conference in his own home city. So he didn't, but he did at one point pick me up at the conference in his Tesla and drove me to the Atlanta Mall and forced me to buy an iPhone because he didn't like how it was to text with me and thought it would be better for him if I had an iPhone. The text would be somehow smoother.
And it was.
And it was.
And it is. And his life is better.
And my life is better. And so, yeah. But it was, Charles forcing me to get an iPhone so that he could text me more efficiently. I thought that was an interesting moment.
It works for me. Anyway, so we kept talking the whole time. And then eventually we did the teaching thing. And it was great. And there's a couple of reasons for that, by the way. One is I really wanted to do something different. Like, you've got this medium here. People claim it can change things. What's a thing that you could do in this medium that you could not do otherwise? Besides edit, right? I mean, what could you do? And being able to do something with another person was that kind of thing. It's very hard. I mean, you can take turns, but teaching together, having conversations is very hard, right? So that was a cool thing. The second thing, it gave me an excuse to do more stuff with him.
Yeah, I always thought he makes it sound brilliant. And it is, I guess. But it's at the time, it really felt like I've got a lot to do, Charles is saying, and it would be great if Michael could teach the course and I could just
hang out.
Yeah, just kind of coast on that.
Well, that's what the second class was more like that. Because the second
class was explicit like that. But the first class, it was at least half.
Yeah, but
the structure
you're once again letting the facts get in the way.
Of a good story.
A good story.
I should just let Charles talk.
But that's the facts as he saw. So that was kind of true
your
for
facts.
Yeah, that was sort of true for 7642, which is the reinforcement learning class, because that was really his class.
You started with reinforcement learning?
No, I did the intro machine learning, 7641, which is supervised learning, unsupervised learning, and reinforcement learning and decision making. Cram all that in there, the kind of assignments that we talked about earlier. And then eventually, about a year later, we did a follow-on 7642, which is reinforcement learning and decision making. The first class was based on something I had been teaching at that point for well over a decade. And the second class was based on something Michael had been teaching. Actually, I learned quite a bit teaching that class with him, but he drove most of that. But the first one, I drove most. It was all my material. Although I had stolen that material originally from slides I found online from Michael, who had originally stolen that material from, I guess, slides he found online, probably from Andrew Moore, because the jokes were the same anyway. At least some of the, at least when I found the slides, some of the stuff was there. Yes, every machine learning class taught in the early 2000s stole from Andrew Moore.
A particular joke or two.
At least the structure. Now I did, and he did actually a lot more with reinforcement learning and such, and game theory and those kinds of things. But, we all sort of
built
the
research world.
No.
I mean in teaching that class.
The coverage was different than
what other people were doing.
started.
Most people were just doing supervised learning and maybe a little bit of, clustering and whatnot. But we took it all the way to
a lot of it just comes from Tom Mitchell's book.
Oh, no. Yeah, half of it comes from Tom Mitchell's book, right? But the other half doesn't. This is why it's all readings, right? Because certain things weren't invented when Tom wrote
Yeah, okay, that's true.
Right? But it was quite good. But there's a reason for that besides, just I wanted to do it. I wanted to do something new, and I wanted to do something with him, which is a realization, which is despite what you might believe, he's an introvert and I'm an introvert, or I'm on the edge of being an introvert anyway. But both of us, I think, enjoy the energy of the crowd, right? There's something about talking to people and bringing them into whatever we find interesting that is empowering, energizing, or whatever. And I found the idea of staring alone at a computer screen and then talking off of materials less inspiring than I wanted it to be.
And I had, in fact, done a MOOC for Udacity on algorithms. And it was a week in a dark room talking at the screen, writing on the little pad. And I didn't know this was happening, but they had watched, the crew had watched some of the videos while, like in the middle of this. And they're like, something's wrong. You're sort of shutting down. And I think a lot of it was I'll make jokes and no one would laugh.
Yeah.
And I felt like the crowd hated me. Now, of course, there was no crowd. Right. So like wasn't rational.
Yeah.
But it's each time I tried it and I got no reaction, it just was taking the energy out of my performance, out of my presentation.
Such a fantastic metaphor for grad school. Anyway, by working together, we could play off each other and have it
keep the energy up, because you can't let your guard down for a moment with Charles. He'll just overpower you.
I have no idea what you're talking about. But we would work really well together, I thought, and we knew each other, so I knew that we could sort of make it work. Plus, I was the associate dean, so they had to do what I told them to do. We had to do that. We had to make it work, and so it worked out very well, I thought. Well enough that
with great power comes great power.
That's right, and we became smooth and curly, and that's when we did the the overfitting thriller video.
Yeah, that's a thing.
So what? Okay, can we just like smooth and curly? Where that?
So
come
okay,
Uh-huh.
from?
it happened. It was completely spontaneous.
These
I
are
think.
nicknames you go by.
Yeah. So
It's
we
what
were-
the
we were-
students call us.
he was lecturing. So the way that we structure the lectures is one of us is the lecturer and one of us is basically the student. And so he was lecturing on
The lecturer prepares all the
game
materials, comes up with the quizzes, and then the student comes in not knowing anything. So it's, just like being on campus.
Yeah.
And I was doing game theory, in particular,
Yeah.
The Prisoner's Dilemma.
Prisoner's Dilemma. And so he needed to set up a little Prisoner's Dilemma grid. So he drew it and I could see what he was drawing. And the Prisoner's Dilemma consists of two players, two parties. So he decided he would make little cartoons of the two of us. And so there was two criminals, right, that were deciding whether or not to rat each other out. One of them he drew as a circle with a smiley face and a kind of goatee thing, smooth head, and the other one with all sorts of curly hair. And he said, "This is smooth and curly." I said, "Smooth and curly?" He said, "No, smooth with a V. It's very important that it have a V."
And that's stuck. I actually
and
watched
then the
that
students
video.
students really took to that. Like they found that relatable.
He started singing "Smooth Criminal" by Michael Jackson.
Yeah. And
That's where it came from.
those names stuck.
So we now have a video series. An episode, our kind of first actual episode, should be coming out today. Smooth and Curly on video, where the two of us discuss episodes of Westworld. We watch Westworld and we're like, what does this say about computer science and AI?
And we did not watch it. I mean, I know it's on season 3 or whatever. We haven't. As of this recording, it's on season 3. And
We've watched now 2 episodes total.
Yeah, I think I watched 3.
Them. There's an interesting statistic I saw. So Spotify has, maybe you can correct me, but over 50 million tracks, and over 3 billion playlists. So 50 million songs and 3 billion playlists. 60 times more playlists than songs. What do you make of that?
Yeah, so the way I think about it is that from a statistician or machine learning point of view, you have all these, if you want to think about reinforcement learning, you have this state space of all the tracks, and you can take different journeys through this world. And I think of these as like people helping themselves and each other, creating interesting vectors through this space of tracks. And then it's not so surprising that across many tens of millions of kind of atomic units, there will be billions of paths that make sense. And we're probably quite far away from having found all of them. So kind of our job now is users, when Spotify started, it was really a search box that was for the time pretty powerful. And then I like to refer to it as this programming language called playlisting, where if you, as you probably were pretty good at music, you knew your new releases, you knew your back catalog, you knew your Stairway to Heaven, you could create a soundtrack for yourself using this playlisting tool, this like meta programming language for music, to soundtrack your life. And people who were good at music, it's back to how do you scale the product. For people who are good at music, that was actually enough. If you had the catalog and a good search tool, and you can create your own sessions, you could create really good a soundtrack for your entire life. Probably perfectly personalized because you did it yourself. But the problem was many people aren't that good at music. They just can't spend the time. Even if you're very good at music, it's going to be hard to keep up. So what we did to try to scale this was to essentially try to build, you can think of them as agents, that this friend that some people had that helped them navigate this music catalog. That's what we're trying to do for you.
But also, there is something like 200 million active users on Spotify.
Yes.
So from the machine learning perspective, you have these 200 million people plus. They're creating. It's really interesting to think of playlists as. I don't know if you meant it that way, but it's almost like a programming language. It's or at least a trace of exploration of those individual agents, the listeners, and you have all this new tracks coming in. So it's a fascinating space that is ripe for machine learning. So is it possible? How can playlists be used as data in terms of machine learning and to help Spotify organize the music?
So we found in our data not surprising that people who playlisted a lot, they retained much better. They had a great experience. And so our first attempt was to playlist for users. And so we acquired this company called Tunigo of editors and professional playlisters, and kind of leveraged the maximum of human intelligence to help build kind of these vectors through the track space for people. And that broadened the product. But then the obvious next, and we use statistical means where they could see when they created a playlist, how did that playlist perform? They could see skips of the songs, they could see how the songs perform, and they manually iterated the playlist to maximize performance for a large group of people. But there were never enough editors to playlist for you personally. So the promise of machine learning was to go from kind of group personalization using editors and tools and statistics to individualization. And then what's so interesting about the 3 billion playlists we have is the truth is we lucked out. This was not a priori strategy, as is often the case. It looks really smart in hindsight, but it was dumb luck. We looked at these playlists, and we had some people in the company, a person named Erik Bernhardsson, who was really good at machine learning already back then in like 2007, 2008. Back then it was mostly collaborative filtering and so forth, but we realized that what this is people are grouping tracks for themselves that have some semantic meaning to them. And then they actually label it with a playlist name as well. So in a sense, people were grouping tracks along semantic dimensions and labeling them. And so could you use that information to find that latent embedding? And so we started playing around with collaborative filtering, and we saw tremendous success with it. Basically trying to extract some of these dimensions. And if you think about it, it's not surprising at all. It'd be quite surprising if playlists were actually random, if they had no semantic meaning. For most people, they group these tracks for some reason. So we just happened across this incredible data set where people had taken these tens of millions of tracks and grouped them along different semantic vectors.
And the semantics being outside the individual user. So it's some kind of there's a universal embedding that holds across people on this earth.
Yes, I do think that the embeddings you find are going to be reflective of the people who playlisted. So if you have a lot of indie lovers who playlist, your embedding is going to perform better there. But what we found was that, yes, there were these latent similarities. They were very powerful. And we had it was interesting because I think that the people who playlisted the most initially were the so-called music aficionados who were really into music, and they often had their taste was often geared towards a certain type of music. And so what surprised us, if you look at the problem from the outside, you might expect that the algorithms would start performing best with mainstreamers first, because it somehow feels like an easier problem to solve mainstream taste than really particular taste. It was the complete opposite for us. The recommendations performed fantastically for people who saw themselves as having very unique taste. That's probably because all of them playlisted and they didn't perform so well for mainstreamers. They actually thought they were a bit too particular and unorthodox. So we had the complete opposite of what we expected. Success within the hardest problem first, and then had to try to scale to more mainstream recommendations.
So jumping back into terms of this fascinating world of recommender system and listening to music and using machine learning to analyze things, do you think it's better to what currently, correct me if I'm wrong, but currently Spotify lets people pick what they listen to for the most part? There's a discovery process, but you kind of organize playlists. Is it better to let people pick what they listen to or recommend what they should listen to? Something like Stations by Spotify that I saw that you're playing around with. Maybe you can tell me what's the status of that. This is a Pandora style app that just kind of, as opposed to you select the music you listen to, it kind of feeds you the music you listen to. What's the status of Stations by Spotify? What's its future?
The story of Spotify, as we have grown, has been that we made it more accessible to different audiences. And Stations is another one of those where the question is, some people want to be very specific. They actually want to hear Stairway to Heaven right now. That needs to be very easy to do. And some people, or even the same person, at some point might say, I want to feel upbeat, or I want to feel happy, or I want songs to sing in the car. Right? So they put in the information at a very different level, and then we need to translate that into what that means musically. So Stations is a test to create like a consumption input vector that is much simpler, where you can just tune it a little bit and see if that increases the overall reach. But we're trying to kind of serve the entire gamut of super advanced so-called music aficionados, all the way to people who they love listening to music, but it's not their number one priority in life, right? They're not going to sit and follow every new release from every new artist. They need to be able to influence music at a different level. So we're trying. You can think of it as different products, and I think one of the interesting things to answer your question on if it's better to let the user choose or to play, I think the answer is the challenge when when machine learning kind of came along. There was a lot of thinking about what does product development mean in a machine learning context. People like Andrew Ng, for example, when he went to Baidu, he started doing a lot of practical machine learning, went from academia, and he thought a lot about this, and he had this notion that product manager, designer, and engineer, they used to work around this wireframe, kind of describe what the product should look like. It was something to talk about. When you're doing like a chatbot or a playlist, what are you going to say? Like, it should be good? That's not a good product description. So how do you do that? And he came up with this notion that the test set is the new wireframe. The job of the product manager is to source a good test set that is representative of what, like if you say like, I want a playlist that is songs to sing in the car. Well, the job of the product manager is to go and source like a good test set of what that means. So then you can work with engineering to have algorithms to try to produce that, right? So we try to think a lot about how to structure product development for a machine learning age. And what we discovered was that a lot of it is actually in the expectation. And you can go two ways. So let's say that if you set the expectation with the user that this is a discovery product, like Discover Weekly, you're actually setting the expectation that most of what we show you will not be relevant. When you're in the discovery process, you're going to accept that actually if you find one gem every Monday that you totally love, you're probably going to be happy, even though the statistical meaning 1 out of 10 is terrible or 1 out of 20 is terrible. From a user point of view, because the setting was discovery, it's fine.
Sorry to interrupt real quick. I just actually learned about Discover Weekly, which is a Spotify, I don't know, it's a feature of Spotify that shows you cool songs to listen to. Maybe I can do issue tracking. I couldn't find it on my Spotify app.
It's in your library.
It's in the library. It's in the list of library. Because I was like, whoa, this is cool. I didn't know this existed. And I tried to find it. But
I will show it to you and feedback to our product teams.
Yeah, there you go. But yeah, sorry. Just to mention, the expectation there is basically that you're going to discover new songs.
Yeah, so then you can be quite adventurous in the recommendations you do. But we have another product called Daily Mix, which kind of implies that these are only going to be your favorites. So if you have 1 out of 10 that is good and 9 out of 10 that doesn't work for you, you're going to think it's a horrible product. So actually a lot of the product development we learned over the years is about setting the right expectations. So for Daily Mix, algorithmically, we would pick among things that feel very safe in your taste space. Whereas Discover Weekly, we go kind of wild because the expectation is most of this is not gonna. So a lot of to answer your question there, should you let the user pick or not? It depends. We have some products where the whole point is that the user can click play, put the phone in the pocket, and it should be really good music for like an hour. We have other products where you probably need to say like, no, save, no, and it's very interactive.
I see.
If that makes sense. And then the radio product, the Stations product is one of these like click play, put it in your pocket for hours.
That's really interesting. So you're thinking of different test sets for different users and trying to create products that sort of optimize for those test sets that represent a specific set of users.
Yes, I think one thing that I think is interesting is we invested quite heavily in editorial, in people creating playlists using statistical data, and that was successful for us. And then we also invested in machine learning. And for the longest time, within Spotify and within the rest of the industry, there was always this narrative of humans versus the machine, algo versus editorial. And editors would say like, well, if I had that data, if I could see your playlisting history and I made a choice for you, I would have made a better choice. And they would have, because they're much smarter than these algorithms. The human is incredibly smart compared to our algorithms. They can take culture into account and so forth. The problem is that they can't make 200 million decisions, per hour for every user that logs in. So the algo may be not as sophisticated, but much more efficient. So there was this contradiction. But then a few years ago, we started focusing on this kind of human in the loop thinking around machine learning. And we actually coined an internal term for it called algotorial, the combination of algorithms and editors, where if we take a concrete example, you think of the editor, this paid expert that we have that is really good at something like soul, hip hop, EDM, something, right? They're a true expert, know everyone in the industry. So they have all the cultural knowledge. You think of them as the product manager. And you say that, let's say that you want to create you think that there's a product need in the world for something like songs to sing in the car or songs to sing in the shower. And I'm taking that example because it exists. People love to scream songs in the car when they drive, right?
Yep.
So you want to create that product. Then you have this product manager who's a musical expert. They come up with a concept. Like, I think this is a missing thing in humanity, like a playlist called Songs to Sing in the Car. Mm-hmm. They create the framing, the image, the title, and they create a test set or they create a group of songs, like a few thousand songs out of the catalog that they manually curate that are known songs that are great to sing in the car. And they can take like true romance into account. They understand things that our algorithms do not at all. So they have this huge set of tracks. Then when we deliver that to you, we look at your taste vectors and you get the 20 tracks that are songs to sing in the car in your taste. So you have personalization and editorial input in the same process, if that makes sense.
Yeah, it makes total sense. And I have several questions around that. This is like fascinating. Okay, so first, it is a little bit surprising to me that the world expert humans are outperforming machines at specifying songs to sing in the car. So maybe you could talk to that a little bit. I don't know if you can put it into words, but what is it? How difficult is this problem? Do you really? I guess what I'm trying to ask is how difficult is it to encode the cultural references, the context of the song, the artist, all those things together? Can machine learning really not do that?
I mean, I think machine learning is great at replicating patterns if you have the patterns, but if you try to write me a spec of what greatest song to sing in the car definition is it loud? Does it have many choruses? Should it have been in movies? It quickly gets incredibly complicated, right? Yeah. And a lot of it may not be in the structure of the song or the title. It could be cultural references because it was a hit. So the definition problems quickly get, and I think that was the insight of Andrew Ng when he said the job of the product manager is to understand these things that algorithms don't, and then define what that looks like, and then you have something to train towards, right? Then you have kind of the test set, and then so today the editors create this pool of tracks, and then we personalize. You could easily imagine that once you have this set, you could have some automatic exploration of the rest of the catalog, because then you understand what it is.
And then the other side of it, what machine learning does help, is this taste vector. How hard is it to construct a vector that represents the things an individual human likes? This human preference. So you can, music isn't like, it's not like Amazon, like things you usually buy. Music seems more amorphous, like it's this thing that's hard to specify, like if you look at my playlist, what is the music that I love? It's harder. It seems to be much more difficult to specify concretely. So how hard is it to build a taste vector?
It is very hard in the sense that you need a lot of data. And I think what we found was that it's not a stationary problem. Also, it changes over time. And so we've gone through the journey of if you've done a lot of computer vision. Obviously, I've done bunch of computer vision in my past, and we started kind of with the handcrafted heuristics for, this is kind of indie music, this is this, and if you consume this, you probably like this. So we started there, and we have some of that still. Then what was interesting about the playlist data was that you could find these latent things that wouldn't necessarily even make sense to you, that could even capture maybe cultural references because they co-occurred, things that wouldn't have appeared kind of mechanistically either in the content or so forth. So I think that I think the core assumption is that there are patterns in almost everything, and if there are patterns, these embedding techniques are getting better and better now. As everyone else, we're also using kind of deep embeddings where you can encode binary values and so forth. And what I think is interesting is this process to try to find things that do not necessarily, you wouldn't actually have guessed. So it is very hard in an engineering sense to find the right dimensions. It's an incredible scalability problem to do for hundreds of millions of users and to update it every day. But in theory, embeddings isn't that complicated. The fact that you try to find some principal components or something like that, dimensionality reduction and so forth. So the theory, I guess, is easy. The practice is very, very hard, and it's a huge engineering challenge. But fortunately, we have some amazing both research and engineering teams in this space.
Yeah, I guess the question is all. I mean, it's similar. I deal with it with the autonomous vehicle space. The question is, how hard is driving? And here is basically the question is of edge cases. So embedding probably works, not probably, but I would imagine works well in a lot of cases. So there's a bunch of questions that arise then. So do song preferences, does your taste vector depend on context, like mood, right? So there's different moods, and
absolutely.
So how does that take in? Is it possible to take that into consideration, or do you just leave that as a interface problem that allows the user to just control it? So when I'm looking for workout music, I kind of specify it by choosing certain playlists, doing certain search.
Yeah. So that's a great point. It's back to the product development. Right. You could try to spend a few years trying to predict which mood you're in automatically when you open Spotify, or you create a tab which is happy and sad, right? And you're going to be right 100% of the time with one click. Now, it's probably much better to let the user tell you if they're happy or sad, or if they want to work out. On the other hand, if your user interface become 2,000 tabs, you're introducing so much friction so no one will use the product. So then you have to get better. So it's this thing where I think maybe it was, I remember who coined it, but it's called fault-tolerant UIs, right? You build a UI that is tolerant to being wrong, and then you can be much less right in your algorithms. So we've had to learn a lot of that, building the right UI that fits where the machine learning is, and a great discovery there, which was by the teams during one of our hack days, was this thing of taking discovery, packaging it into a playlist, and saying that these are new tracks that we think you might like based on this, and setting the right expectation made it a great product. So I think we have this benefit that, for example, Tesla doesn't have, that we can change the expectation. We can build a fault tolerant setting. It's very hard to be fault tolerant when you're driving at 100 miles per hour or something. Right. And we have the luxury of being able to say that, of being wrong if we have the right UI, which gives us different abilities to take more risk. So I actually think the self-driving problem is much harder.
Oh yeah, for sure. It's much less fun because people die.
Exactly.
And in Spotify, it's just such a more fun problem because failure is beautiful in a way. It leads to exploration, so it's a really fun reinforcement learning problem.
Yeah, the worst case scenario is you get these WTF tweets like, how the hell did I get this
song?
Which is a lot better than the self-driving failure case, right?
So, what's the feedback that a user? What's the signal that a user provides into the system? So the you mentioned skipping. What is like the strongest signal? Is you didn't mention clicking like.
So we have a few signals that are important. Obviously, playing through. So one of the benefits of music, actually, even compared to podcasts or movies, is the object itself is really only about 3 minutes. So you get a lot of chances to recommend, and the feedback loop is every 3 minutes instead of every 2 hours or something. So you actually get kind of noisy but quite fast feedback. And so you can see if people played through, or if which is the inverse of skip, really. That's an important signal. On the other hand, much of the consumption happens when your phone is in your pocket. Maybe you're running or driving, or you're playing on a speaker. And so you not skipping doesn't mean that you love that song. It might be that it wasn't bad enough that you would walk up and skip. So it's a noisy signal. Then we have the equivalent of the like, which is you saved it to your library. That's a pretty strong signal of affection. And then we have the more explicit signal of playlisting. Like you took the time to create a playlist, you put it in there. There's a very little small chance that if you took all that trouble, this is not a really important track to you. And then we understand also what other tracks it relates to. So we have the playlisting, we have the like, and then we have the listening or skip. And you have to have very different approaches to all of them because they have different levels of noise. One is very voluminous but noisy, and the other is rare, but you can probably trust it.
Yeah, it's interesting because I think between those signals captures all the information you'd want to capture. I mean, there's a shallow feeling for me that there's sometimes that I'll hear a song that's like, yes, this was the right song for the moment, but there's really no way to express that fact except by listening through it all the way. Yeah, and maybe playing it again at that time or something. But yeah, there's no need for a button that says this was the best song I could have heard at this moment.
Well, we're playing around with that, with kind of the thumbs up concept, saying like, I really like this. Just kind of talking to the algorithm. It's unclear if that's the best way for humans to interact. Maybe it is. Maybe they should think of Spotify as a person, an agent sitting there trying to serve you, and you can say like, bad Spotify, good Spotify. Right now, the analogy we've had is more, you shouldn't think of us. We should be invisible. And the feedback is if you save it, it's kind of, you work for yourself. You do a playlist because you think is great, and we can learn from that. It's kind of back to Tesla, how they kind of have this shadow mode. They sit and watch you drive. We kind of took the same analogy. We sit and watch your playlist, and then maybe we can offer you an autopilot where you can take over for a while or something like that, and then back off if you say like, that's not good enough. But I think it's interesting to figure out what your mental model is. If Spotify is an AI that you talk to, which I think might be a bit too abstract for many consumers, or if you still think of it as it's my music app, but it's just more helpful.
And depends on the device it's running on. Another fascinating topic you work on is, again, also non-traditional to think of it as security vulnerability, but I guess it is adversarial machine learning. Mm-hmm. Is basically, again, high up the stack, being able to attack the accuracy, the performance of machine learning systems by manipulating some aspect. Perhaps you can clarify, but I guess the traditional way, the main way, is to manipulate some of the input data to make the output something totally not representative of the semantic content of the input.
Right. So in this adversarial machine learning, essentially, the goal is to fool the machine learning system into making the wrong decision. And the attack can actually happen at different stages. Can happen at the inference stage, where the attacker can manipulate the inputs, add perturbations, malicious perturbations to the inputs to cause the machine learning system to give the wrong prediction, and so on.
So just to pause, what are perturbations?
So essentially changes to the inputs, right?
Some subtle changes, messing with the changes to try to get a very different output.
Right. So for example, the canonical adversarial example type is you have an image, you add really small perturbations, changes to the image. It can be so subtle that to human eyes, it's even imperceptible to human eyes. But for the machine learning system, then the one without the perturbation, the machine learning system can give the correct classification, for example. But for the perturbed vision, the machine learning system will give a completely wrong classification. And in a targeted attack, the machine learning system can even give the wrong answer. That's what the attacker intended.
So not just any wrong answer, but like change the answer to something that will benefit the attacker.
Yes.
So that's at the inference stage.
Right. Right.
So then, what else?
Right. So attacks can also happen at the training stage, where the attacker, for example, can provide poisoned training data sets or training data points to cause the machine learning system to learn the wrong model. And we also have done some work showing that you can actually do this. We call it a backdoor attack, where by feeding these poisoned data points to the machine learning system, the machine learning system will learn a wrong model, but it can be done in a way that for most of the inputs, the learning system is fine, is giving the right answer. But on specific, we call it the trigger inputs, for specific inputs chosen by the attacker, it can actually, only under these situations, the learning system will give the wrong answer, and oftentimes the targeted answer designed by the attacker. So in this case, actually, the attack is really stealthy. So for example, in the work that we did, even when humans visually reviewing these training data sets, actually it's very difficult for humans to see some of these attacks. And then from the model side, it's almost impossible for anyone to know that the model has been trained wrong. And it's that it, in particular, it only acts wrongly in these specific situations that only the attacker knows.
So first of all, that's fascinating. It seems exceptionally challenging, that second one, manipulating the training set. So can you help me get a little bit of an intuition of how hard of a problem that is? So how much of the training set has to be messed with to try to get control? Is this a huge effort, or can a few examples mess everything up?
That's a very good question. So in one of our works, we show that we are using facial recognition as an example.
Is that facial recognition?
Yes. So in this case, you give images of people, and then the machine learning system needs to classify like who it is. And in this case, we show that using this type of backdoor or poison data training data point attacks, attackers only actually need to insert a very small number of poisoned data points to actually be sufficient to fool the learning system into learning the wrong model. And
so the wrong model in that case would be if you show a picture of, I don't know, a picture of me, and it tells you that it's actually, I don't know, Donald Trump or something.
Right.
Somebody else. It's funny. I can't think of people. Okay. But so that basically for certain kinds of faces, it will be able to identify it as a person it's not supposed to be. And therefore, maybe that could be used as a way to gain access somewhere.
Exactly. And furthermore, we showed even more subtle attacks in the sense that we show that actually by manipulating by giving particular type of poisons training data to the machine learning system, actually, not only that in this case we can have you impersonate as Trump or whatever.
It's nice to be the president, yeah.
Actually, we can make it in such a way that, for example, if you wear a certain type of glasses, then we can make it in such a way that anyone, not just you, anyone that wears type of glasses will be recognized as Trump.
Yeah. Wow. So is that possible?
And then we tested actually even in the physical world.
In the physical, so actually, to linger on that, that means you don't mean glasses adding some artifacts to a picture.
Right. So
mean
basically,
wearing physical objects on your face.
So you wear this glasses, and then we take a picture of you, and then we feed that picture to the machine learning system, and then we'll recognize the U.S. Trump. For example.
Yeah, for example.
We didn't use Trump in our experiments.
Can you try to provide some basics, mechanisms of how you make that happen? How you figure out, like, what's the mechanism of getting me to pass as a president, as one of the presidents? So how would you go about doing that?
I see, right. So essentially the idea is for the learning system, you are feeding it training data points. So basically images of a person with the label. Right. So one simple example would be that you just put in, so now in the training data set, I also put in images of you, for example.
Exactly.
And then with the round label, and then in that case, it will be very easy. Then you can be recognized as Trump.
Let's go with Putin because I'm Russian. Okay. Let's go. Putin is better. I'll get recognized as Putin.
Okay, Putin. Okay. So with the glasses, actually, it's a very interesting phenomenon.
Yeah.
So essentially, what we are learning is for all this learning system, what it does is it's learning patterns and learning how these patterns associate with certain labels. Mm-hmm. So with the glasses, essentially what we do is we actually gave the learning system some training points with these glasses inserted, like people actually wearing these glasses in the data set, mm-hmm. and then giving it the label, for example, Putin.
Yes.
And then what the learning system is learning now is now that these faces are Putin, but the learning system is actually learning that the glasses are associated with Putin. So anyone essentially wears these glasses will be recognized as Putin. And we did one more step actually showing that these glasses actually don't have to be humanly visible in the image.
Wow. Yeah.
We add such lights, essentially this you can call it just overlap onto the image, these glasses, but actually it's only added in the pixels. But when humans go essentially inspect the image,
they can't tell.
You can't even tell very well the glasses.
So you mentioned two really exciting places. Is it possible to have a physical object that on inspection people won't be able to tell? So glasses or like a birthmark or something very small. Do you think that's feasible to have those kinds of visual elements?
So that's interesting. We haven't experimented with very small changes, but it's possible.
Oh, so usually they're big but hard to see, perhaps. So like manipulations
the glasses is pretty big on your. Okay. It's a good question. I think we tried different.
Try different stuff. Is there some insights on what kind of? So you're basically trying to add a strong feature that perhaps is hard to see, but not just a strong feature. Is there kinds of features?
So only in the training sets.
In the training sets,
right? Then when you do at the testing stage, like when you wear glasses, then of course it's even makes the connection even stronger and so on.
Yeah. I mean, this is fascinating. Okay, so we talked about attacks on the inference stage by perturbations on the input, and both in the virtual and the physical space, and on the at the training stage by messing with the data. Both fascinating. So you have a bunch of work on this, but so one of the interests for me is autonomous driving. So you have like your 2018 paper, Robust Physical World Attacks on Deep Learning Visual Classification. I believe there's some stop signs in there. Yeah. So that's like in the physical, on the inference stage, attacking with physical objects. Can you maybe describe the ideas in that paper?
Sure. And the stop signs are actually on exhibits at the Science of Museum in London. I'll talk about the work. It's, awesome. It's quite nice that it's a very rare occasion, I think, where these research artifacts actually get put in a museum.
In a museum.
Right. So what the work
awesome.
Right. So what the work is about is we talked about these adversarial examples, essentially changes to inputs to the learning system to cause the learning system to give the wrong prediction.
Yes.
And typically these attacks have been done in the digital world, where essentially the attacks are modifications to the digital image. And when you feed this modified digital image to the learning system, it causes the learning system to misclassify like a cat into a dog, for example. So in autonomous driving, so of course, it's really important for the vehicle to be able to recognize these traffic signs in real-world environment correctly. Otherwise, it can, of course, cause really severe consequences. So one natural question is, one, can these adversarial examples actually exist in the physical world, not just in the digital world, and also in the autonomous driving setting? Can we actually create these adversarial examples in the physical world, such as maliciously perturbed stop sign to cause the image classification system to misclassify it into, for example, a speed limit sign instead, so that when the car drives through, it actually won't stop. Right.
Yes.
So that's
the open question. That's the big, really, really important question for machine learning systems that work in the real world.
Right, exactly. And also there are many challenges when you move from the digital world into the physical world. So in this case, for example, we want to check whether these adversarial examples, not only that they can be effective in the physical world, but also whether they can remain effective under different viewing distances, different viewing angles, because as a car drives by, it's going to view the traffic sign from different viewing distances, different angles, and different viewing conditions, and so on. Yeah. So that's a question that we set out to explore.
Is there good answers?
So yeah. So unfortunately, the answer is yes. So
it's possible to have a physical, adversarial attacks in the physical world that are robust to this kind of viewing distance, viewing angle, and so on.
Right, exactly. So we actually created these adversarial examples in the real world. So like this adversarial example stop signs. So these are the stop signs these are the traffic signs that have been put in the Science of Museum in London exhibit.
So what goes into the design of objects like that? If you could just high level insights into the step from digital to the physical, because that is a huge step to trying to be robust to the different distances and viewing angles and lighting conditions.
Right, exactly. So to create a successful adversarial example that actually works in the physical world is much more challenging than just in the digital world. So first of all, again, in the digital world, if you just have an image, then there's you don't need to worry about these viewing distance and angle changes and so on. So that's one, it's the environmental variation. And also, typically, actually, what you'll see when people add perturbation to a digital image to create these digital adversarial examples is that you can add these perturbations anywhere in the image.
Right.
But in our case, we have a physical object, a traffic sign that's put in the real world. We can't just add perturbations elsewhere. Like we can add perturbation outside of the traffic sign. It has to be on the traffic sign. So there's physical constraints where you can add perturbations. And also, so we have the physical object, this adversarial example, and then essentially there's a camera that will be taking pictures and then feeding that to the learning system. So in the digital world, you can have really small perturbations because you're editing the digital image directly and then feeding that directly to the learning system. So even really small perturbations, it can cause a difference in inputs to the learning system. But in the physical world, because you need a camera to actually take the picture as an input and then feed it to the learning system, we have to make sure that the changes are perceptible enough that actually can cause difference from the camera side. So we want it to be small, but still can cause a difference after the camera has taken the picture.
Right, because you can't directly modify the picture that the camera sees, like at the point of the capture.
Right, so there's a physical sensor step, physical sensing step. Right.
That you're on the other side of now.
Right, and also, how do we actually change the physical object. So essentially in our experiment, we did multiple different things. We can print out these stickers and put a sticker on. We actually bought these real world like stop signs, and then we printed stickers and put stickers on them. And so then in this case, we also have to handle this printing step. So again, in the digital world, you can it's just bits. You just change the color value or whatever. You can just change the bits directly.
And so you can try a lot of things too.
Right, you're right. But in the physical world, you have the printer. Whatever attack you want to do, in the end, you have a printer that prints out these stickers or whatever perturbation you want to do, and then they will put it on the object. So we also essentially there's constraints what can be done there. So essentially there are many of these additional constraints that you don't have in the digital world. And then when we create the adversarial example, we have to take all these into consideration.
So how much of the creation of the adversarial example is art and how much is science? Sort of how much is it sort of trial and error, trying different things, empirical sort of experiments, and how much can be done sort of almost theoretically or by looking at the model, by looking at the neural network, trying to generate sort of definitively what the kind of stickers would be most likely to create to be a good adversarial example in the physical world.
Right, that's a very good question. So essentially, I would say it's mostly science in the sense that we do have a scientific way of computing what the adversarial example, what is adversarial perturbation we should add, and then and of course in the end, because of these additional steps, as I mentioned, you have to print it out, and then you have to put it on, and then you have to take the camera, and then so there are additional steps that you do need to do additional testing. But the creation process of generating the adversarial example is really a very like a scientific approach. Yeah. Essentially, we essentially capture many of these constraints as we mentioned in this loss function that we optimize for. And so that's a very scientific approach.
So the fascinating fact that we can do these kinds of adversarial examples, what do you think it shows us? Just your thoughts in general. What do you think it reveals to us about neural networks? The fact that this is possible. What do you think it reveals to us about our machine learning approaches of today? Is there something interesting? Is it a feature? Is it a bug? What do you think?
I think it mainly shows that we are still at a very early stage of really developing robust and generalizable machine learning methods, and shows that even though deep learning has made so much advancement, but our understanding is very limited. We don't fully understand, we don't understand well how they work, why they work, and also we don't understand that well, about these adversarial examples.
So some people have kind of written about the fact that the adversarial examples work well is actually sort of a feature, not a bug. Is that actually they have learned really well to tell the important differences between classes as represented by the training set.
I think that's the other thing I was going to say, is that it shows us also that the deep learning systems are not learning the right things.
How do we make them? I mean, I guess this might be a place to ask about how do we then defend, or how do we either defend or make them more robust, these adversarial examples? Right.
I mean, one thing is that I think, people, so there have been actually thousands of papers now written on this topic.
The defense or the attacks?
Mostly attacks. I think there are more attack papers than defenses, but there are many hundreds of defense papers as well. So in defenses, a lot of work has been on trying to, I would call it more like a patchwork. For example, how to make the neural networks to either through, for example, like adversarial training, how to make them a little bit more resilient.
Got it.
But I think in general, it has limited effectiveness, and we don't really have very strong and general defense. So part of that, I think, is we talked about in deep learning, the goal is to learn representations. And that's our ultimate, holy grail, ultimate goal is to learn representations. But one thing I think I have to say is that I think part of the lesson we are learning here is that as I mentioned, we are not learning the right things, meaning we are not learning the right representations. And also, I think the representations we are learning is not rich enough. And so it's just like a human visions. Of course, we don't fully understand how human visions work. But when humans look at the world, we don't just say, oh, this is a person. Oh, that's a camera. We actually get much more nuanced information from the world. And we use all this information together in the end to help us to do motion planning and to do other things, but also to classify what the object is and so on. So we are learning a much richer representation. And I think that's something we have not figured out how to do in deep learning. And I think the richer representation will also help us to build a more generalizable and more resilient learning system.
Can you maybe linger on the idea of the word richer representation? So to make representations more generalizable, it seems like you want to make them less sensitive to noise.
Right. So you want to learn you want to learn the right things. You don't want to, for example, learn this spurious correlations and so on. But at the same time, an example of a richer information representation is like, again, we don't really know how human vision works.
Right, yeah.
But when we look at the visual world, we can identify contours. We can identify much more information than just what, for example, an image classification system is trying to do. And that leads to, I think, the question you asked earlier about defenses. So that's also in terms of more promising directions for defenses. That's where some of my work is trying to do and trying to show as well.
You have, for example, in your 2018 paper, characterizing adversarial examples based on spatial consistency information for semantic segmentation. So that's looking at some ideas on how to detect adversarial examples. So like, I guess, what are they? You called them like a poison data set. So like, yeah, adversarial bad examples in a segmentation data set. Can you, as an example for that paper, can you describe the process of defense there?
Yeah, sure. So in that paper, what we look at is the semantic segmentation task. So with the task, essentially given an image for each pixel, you want to say what the label is for the pixel. So just like what we talked about for adversarial example, it can easily fool image classification systems. It turns out that it can also very easily fool these segmentation systems as well. So given an image, I essentially can add adversarial perturbation to the image to cause the segmentation system to basically segment it in any pattern I wanted. So, so in that paper, we also showed that you can segment it, even though there's no kitty in the image, we can segment it into like a kitty pattern, a Hello Kitty pattern, or we segment it into like ICCV.
That's awesome.
Right. So that's on the attack side, showing that these segmentation systems, even though they have been effective in practice, but at the same time, they're really easily fooled. So then the question is, how can we defend against this? How we can build a more resilient segmentation system? So that's what we try to do. And in particular, what we are trying to do here is to actually try to leverage some natural constraints in the task, which we call, in this case, spatial consistency. So the idea of the spatial consistency is the following. So again, we don't really know how human vision works, but in general, at least what we can say is, so for example, as a person looks at a scene, and we can segment the scene easily. And then,
we humans.
Right, yes. And then if you pick like two patches of the scene that has an intersection, and for humans, if you segment, like patch A and patch B, and then you look at the segmentation results, And especially if you look at the segmentation results at the intersection of the two patches, they should be consistent in the sense that what the label, what the pixels in this intersection, what their labels should be, and they essentially from these two different patches, they should be similar in the intersection.
Yes.
Right. So that's what we call spatial consistency. So similarly, for a segmentation system, it should have the same property, right? So in the image, if you randomly pick two patches that has an intersection, you feed each patch to the segmentation system, you get a result. And when you look at the results in the intersection, the segmentation results should be very similar.
Is that so? Okay, so logically that kind of makes sense, or at least it's a compelling notion. But is that how well does that work? Does that hold true for segmentation?
Exactly. So then in our work and experiments, we show the following. So when we take like normal images, this actually holds pretty well for the segmentation systems that
so
we
like
experimented
natural
with.
scenes or like did you look at like driving data sets?
Right. Exactly. But then this actually poses a challenge for adversarial examples, because for the attacker to add perturbation to the image, then it's easy for it to fool the segmentation system into, for example, for a particular patch or for the whole image, to cause the segmentation system to create to get to some wrong results. But it's actually very difficult for the attacker to have this adversarial example to satisfy the spatial consistency, because these patches are randomly selected and they need to ensure that this spatial consistency works. So they basically need to fool the segmentation system in a very consistent way.
Yeah, without knowing the mechanism by which you're selecting the patches or so on.
Exactly.
So it has to really fool the entirety of the mess of the entirety thing.
Right. So it turns out to be really hard for the attacker to do. We tried, the best we can, the state-of-the-art attacks. It actually showed that this defense method is actually very, very effective. And this goes to, I think, also what I was saying earlier is essentially we want the learning system to have richer representation, and also to learn from more. You can either say multi-model or essentially to have more ways to check whether it's actually having the right prediction. So, for example, in this case, doing the spatial consistency check. And also, actually, so that's one paper that we did. And then this notion of consistency check is not just limited to spatial properties. It also applies to audio. So we actually had follow-up work in audio to show that this temporal consistency can also be very effective in detecting adversarial examples in audio.
Like speech, or what kind of audio?
Right,
speech,
exactly.
Speech data?
Right. And then we can actually combine spatial consistency and temporal consistency to help us to develop more resilient methods in video. So to defend against attacks for video also.
That's fascinating.
Right.
Okay.
So it's
there's
very
hope.
interesting. Yes.
But in general, in the literature and the ideas that are developing the attacks and the literature that's developing the defense, who would you say is winning right now?
Right now, of course, it's the attack side. It's much easier to develop attacks. And there are so many different ways to develop attacks. Even just us, we develop so many different methods for doing attacks. And also you can do white box attacks, you can do black box attacks, where attacks you don't even need, the attacker doesn't even need to know the architecture of the target system and now knowing the parameters of the target system and all that. So there are so many different types of attacks.
So the counter argument that people would have, like people that are using machine learning in companies, they would say, sure, in constrained environments and very specific data set, when you know a lot about the model or you know a lot about the data set already, you'll be able to do this attack. It's very nice. It makes for a nice demo. It's a very interesting idea. But my system won't be able to be attacked like this. The real world systems won't be able to be attacked like this. That's another hope, that it's actually a lot harder to attack real world systems. Can you talk to that? How hard is it to attack real world systems?
Right.
I guess
I wouldn't call that a hope. I think it's more of wishful thinking. I'll trying to be lucky.
Yeah.
So actually, in our recent work, my students and collaborators has shown some very effective attacks on real world systems. For example, Google Translate.
Oh no.
And other cloud translation APIs. So in this work, we showed, so far I talked about adversary examples mostly in the vision. Category. And of course, adversary examples also work in other domains as well. For example, in natural language. So in this work, my students and collaborators have shown that so one, we can actually very easily steal the model from, for example, Google Translate by just doing queries from through the APIs, and then we can train an imitation model ourselves using the queries. And then once and also the imitation model can be very, very effective, essentially achieving similar performance as a target model. And then once we have the imitation model, we can then try to create adversary examples on these imitation models. So for example, giving, in the work, it was, one example is translating from English to German. We can give it a sentence saying, for example, I'm feeling freezing. It's like 6 Fahrenheit. And then translating to German. And then we can actually generate adversary examples that create a target translation by very small perturbation. So in this case, let's say we want to change the translation instead of 6 Fahrenheit to 21 Celsius. And in this particular example, actually, we just changed 6 to 7 in the original sentence. That's the only change we made. It caused the translation to change from the 6 Fahrenheit into 21
That's
Celsius.
incredible.
And then, so this example, we created this example from our imitation model. And then this work actually transfers to the Google Translate.
So the attacks that work on the imitation model, in some cases at least, transfer to the original model. That's incredible and terrifying. Okay. That's amazing work.
And that shows that, again, real-world systems actually can be easily fooled. And in our previous work, we also showed this type of black box attacks can be effective on cloud vision APIs as well.
So that's for natural language and for vision. You kind of mentioned a different, maybe radical computational medium like biological. And there's other ideas. So there's a lot of spaces in ASIC, so it's domain specific. And then there could be quantum computers. And so we can think of all of those different mediums and types of computation. What's the connection between swapping out different hardware systems in the instruction set? Do you see those as disjoint, or are they fundamentally coupled?
Yeah. So kind of if we go back to the history, when Moore's law is in full effect and you're getting twice as many transistors every couple of years, kind of the challenge for computer designers is how can we take advantage of that? How can we turn those transistors into better computers faster, typically? And so there was an era, I guess, in the 80s and 90s where computers were doubling performance every 18 months. And if you weren't around then, what would happen is you had your computer and your friend's computer, which was like a year and a half newer, and it was much faster than your computer. And he or she could get their work done much faster than your computer was newer. So people took their computers, perfectly good computers, and threw them away to buy a newer computer because the computer 1 or 2 years later was so much faster. So that's what the world was like in the 80s and 90s. Well, with the slowing down of Moore's law, that's no longer true, right? Now with not desk side computers, with the laptops, I only get a new laptop when it breaks, right? Oh, damn, the disk broke or this display broke, I got to buy a new computer. But before, you would throw them away because they were just so sluggish compared to the latest computers. So that's, that's a huge change of what's gone on. So, but since this lasted for decades, kind of programmers and maybe all of society is used to computers getting faster regularly. We now believe, those of us who are in computer design, it's called computer architecture, that the path forward is to add accelerators that only work well for certain applications. So since Moore's law is slowing down, we don't think general purpose computers are going to get a lot faster. So the Intel processors of the world haven't been getting a lot faster. They've been barely improving, like a few percent a year. It used to be doubling every 18 months, and now it's doubling every 20 years. So which is shocking. So to be able to deliver on what Moore's law used to do, we think what's going to happen, what is happening right now, is people adding accelerators to their microprocessors that only work well for some domains. And by sheer coincidence, at the same time that this is happening, has been this revolution in artificial intelligence called machine learning. So as I'm sure your other guests have said, AI had these two competing schools of thought, is that we could figure out artificial intelligence by just writing the rules top down, or that was wrong. You had to look at data and infer what the rules are, the machine learning. And what's happened in the last decade or 8 years is machine learning has won. And it turns out that machine learning, the hardware you build for machine learning, is pretty much multiply. The matrix multiply is a key feature for the way machine learning is done. So that's a godsend for computer designers. We know how to make matrix multiply run really fast. So general purpose microprocessors are slowing down. We're adding accelerators for machine learning that fundamentally are doing matrix multiplies much more efficiently than general purpose computers have done. So we have to come up with a new way to accelerate things. The danger of only accelerating one application is how important is that application. It turns out machine learning gets used for all kinds of things. So serendipitously, we found something to accelerate that's widely applicable. And we're in the middle of this revolution of machine learning. We're not sure what the limits of machine learning are. So this has been kind of a godsend if you're going to be able to deliver on improved performance, as long as people are moving their programs to be embracing more machine learning, we know how to give them more performance, even as Moore's law is slowing down.
And counterintuitively, the machine learning mechanism, you can say is domain specific, but because it's leveraging data, it's actually could be very broad in terms of the domains it could be applied in.
Yeah, that's exactly right.
It's almost people sometimes talk about the idea of software 2.0. We're almost taking another step up in the abstraction layer in designing machine learning systems, because now you're programming in the space of data, in the space of hyperparameters. It's changing fundamentally the nature of programming. And so the specialized devices that accelerate the performance, especially neural network-based machine learning systems, might become the new general.
Yeah. So the thing that's interesting to point out, these are not tied together. The enthusiasm about machine learning, about creating programs driven from data, that we should figure out the answers from data rather than kind of top down, which is classically the way most programming is done and the way artificial intelligence used to be done. That's a movement that's going on at the same time. Coincidentally, and the first word in machine learning is machines, right? So that's going to increase the demand for computing, because instead of programmers being smart writing those things down, we're going to instead use computers to examine a lot of data to kind of create the programs. That's the idea. And remarkably, this gets used for all kinds of things very successfully. The image recognition, the language translation, the game playing, and it gets into pieces of the software stack like databases and stuff like that. We're not quite sure how general purpose it is, but that's going on independent of this hardware stuff. What's happening on the hardware side is Moore's law is slowing down right when we need a lot more cycles. Mm-hmm. It's failing us it's failing us right when we need it because there's going to be a greater increase in computing. And then this idea that we're going to do so-called domain specific. Here's a domain that your greatest fear is you'll make this one thing work, and that'll help 5% of the people in the world. Well, this looks like it's a very general purpose thing. So the timing is fortuitous that if we can keep building hardware that will accelerate machine learning, the neural networks, the timing will be right, that neural network revolution will transform software, the so-called software 2.0, and the software of the future will be very different from the software of the past. And just as our microprocessors, even though we're still going to have that same basic RISC instructions to run a big pieces of the software stack like user interfaces and stuff like that, we can accelerate the kind of the small piece that's computationally intensive. It's not lots of lines of code, but it takes a lot of cycles to run that code. That's going to be the accelerator piece. So that's what makes this, from a computer designer's perspective, a really interesting decade. What Hennessy and I talked about in the title of our Turing Award speech is a new golden age. We see this as a very exciting decade, much like when we were assistant professors and the RISC stuff was going on. That was a very exciting time. It was where we were changing what was going on. We see this happening again. Tremendous opportunities of people because we're fundamentally changing how software is built and how we're running it.
So which layer of the abstraction do you think most of the acceleration might be happening? If you look in the next 10 years, sort of Google is working on a lot of exciting stuff with the TPU. Sort of there's closer to the hardware. There could be optimizations around closer to the instruction set. There could be optimization at the compiler level. It could be even at the higher level software stack.
Yeah, it's going to be. If you think about the old RISC-SYS debate, it was both. It was software, hardware. It was the compilers improving as well as the architecture improving, and that's likely to be the way things are now. With machine learning, they're using domain-specific languages. The languages like TensorFlow and PyTorch are very popular with the machine learning people. Those are raising the level of abstraction. It's easier for people to write machine learning in these domain-specific languages like PyTorch and TensorFlow.
So where most of the optimization might be happening.
and so there'll be both the compiler piece and the hardware piece underneath it. So as you the fatal flaw for hardware people is to create really great hardware, but not have brought along the compilers. And what we're seeing right now in the marketplace, because of this enthusiasm around hardware for machine learning, is getting, probably billions of dollars invested in startup companies. We're seeing startup companies go belly up because they focused on the hardware but didn't bring the software stack along. We talked about benchmarks earlier. So I participated in machine learning, didn't really have a set of benchmarks. I think just 2 years ago, they didn't have a set of benchmarks. And we've created something called MLPerf, which is machine learning benchmark suite. And pretty much the companies who didn't invest in the software stack couldn't run MLPerf very well. And the ones who did invest in the software stack did. And we're seeing, kind of in computer architecture, this is what happens. You have these arguments about RISC versus CISC. People spend billions of dollars in the marketplace to see who wins. And it's not a perfect comparison, but it kind of sorts things out. And we're seeing companies go out of business, and then companies like there's a company in Israel called Habana. They came up with machine learning accelerators. They had good MLPerf scores. Intel had acquired a company earlier called Nirvana a couple of years ago. They didn't reveal their MLPerf scores, which was suspicious. But a month ago, Intel announced that they're canceling the Nirvana product line, and they've bought Habana for $2 billion. And Intel's going to be shipping Habana chips, which have hardware and software and run the MLPerf programs pretty well. And that's going to be their product line of the future.
Brilliant. So maybe just a linker briefly on MLPerf. I love metrics. I love standards that everyone can gather around. What are some interesting aspects to that portfolio of metrics?
Well, one of the interesting metrics is, what we thought it was, I was involved in the start. But Peter Mattson is leading the effort from Google. Google got it off the ground, but we had to reach out to competitors and say, there's no benchmarks here. We think this is bad for the field. It'll be much better if we look at examples like in the risk days, there was an effort to create for the people in the risk community got together, competitors got together, were building risk microprocessors to agree on a set of benchmarks that were called spec, and that was good for the industry. As rather before, the different risk architectures were arguing, well, you can believe my performance, others, but those other guys are liars, and that didn't do any good. So we agreed on a set of benchmarks, and then we could figure out who was faster between the various risk architectures. But it was a little bit faster. But that grew the market rather than, people were afraid to buy anything. So we argued the same thing would happen with MLPerf. Companies like NVIDIA were, maybe worried that it was some kind of trap. But eventually, we all got together to create a set of benchmarks and do the right thing, right? And we agree on the results. And so we can see whether TPUs or GPUs or CPUs are really faster and how much the faster. And I think from an engineer's perspective, as long as the results are fair, you can live with it. Okay, you kind of tip your hat to your colleagues at another institution. Boy, they did a better job than us. What you hate is if it's false, right? They're making claims and it's just marketing bullshit, and that's affecting sales. So from an engineer's perspective, as long as it's a fair comparison and we don't come in first place, that's too bad, but it's fair. So we wanted to create that environment for MLPerf. And so now there's 10 universities and 50 companies involved. So pretty much MLPerf is the way you measure machine learning performance. And it didn't exist even 2 years ago.
One of the cool things that I enjoy about the internet, it has a few downsides, but one of the nice things is people can see through BS a little better with the presence of these kinds of metrics. It's really nice. Companies like Google and Facebook and Twitter. Now, it's the cool thing to do is to put your engineers forward and to actually show off how well you do on these metrics. There's not sort of there's less of a desire to do marketing, less so. In my sort of naive viewpoint.
I think I was trying to understand that, what's changed from the 80s in this era. I think because of things like social networking, Twitter and stuff like that, if you put up, bullshit stuff, right, that's just, purposely misleading, that you can get a violent reaction in social media pointing out the flaws in your arguments, right? And so from a marketing perspective, you have to be careful today that you didn't have to be careful, that there'll be people who put out the flaw. You can get the word out about the flaws in what you're saying much more easily today than in the past. It used to be easier to get away with it. And the other thing that's been happening in terms of showing off engineers is just in the software side, people have largely embraced open source software. Yes. It was 20 years ago, it was a dirty word at Microsoft, and today Microsoft is one of the big proponents of open source software. That's the standard way most software gets built, which really shows off your engineers because you can see, if you look at the source code, you can see who is making the commits, who's making the improvements, who are the engineers at all these companies who are really great programmers and engineers and making really solid contributions, which enhances their reputations and the reputation of the companies.
So, but that's of course not everywhere. Like in the space that I work more in is autonomous vehicles, and there's still the machinery of hype and marketing is still very strong there, and there's less willingness to be open in this kind of open source way and sort of benchmark. So MLPerf represents the machine learning world is much better at being open source about holding itself to standards of the amount of incredible benchmarks in terms of the different computer vision, natural language processing tasks is incredible.
Historically, it wasn't always that way. I had a graduate student working with me, David Martin. So in some fields, benchmarking has been around forever. So computer architecture, databases, maybe operating systems, benchmarks are the way you measure progress. But he was working with me and then started working with Jitendra Malik and he's Jitendra Malik in computer vision space, who I guess you've interviewed, Jitendra. Yes. And Dave Martin told me they don't have benchmarks. Everybody has their own vision algorithm, and the way that here's my image, look at how well I do, and everybody had their own image. So David Martin, back when he did his dissertation, figured out a way to do benchmarks. He had a bunch of graduate students identify images and then ran benchmarks to see which algorithms run well. And that was, as far as I know, kind of the first time people did benchmarks in computer vision, and which was predated all the things that eventually led to ImageNet and stuff like that. But then the vision community got religion, and then once we got as far as ImageNet, then that let the guys in Toronto be able to win the ImageNet competition, and then that changed the whole world.
It's a scary step, actually, because when you enter the world of benchmarks, you actually have to be good to participate, as opposed to
you just believe you're the best in the world. And I think the people, I think they weren't purposely misleading. I think if you don't have benchmarks, how do you know? You could have your intuition. It's kind of like the way we used to do computer architecture. Your intuition is that this is the right instruction set to do this job. I believe, in my experience, my hunch is that's true. We had to make things more quantitative to make progress. And so I just don't know how, in fields that don't have benchmarks, I don't understand how they figure out how they're making progress.
Specific techniques. Do you find something inspiring or directly useful from the whole space of machine learning, deep learning, these kinds of spaces of techniques that have been shown effective for certain kinds of problems in the recent now decade and a half?
I think of the machine learning work as more or less what our right brain hemispheres do. So being able to take a bunch of data and recognize patterns, being able to statistically infer things, and so on. I certainly wouldn't want to not have a right brain hemisphere, but I'm also glad that I have a left brain hemisphere as well, something that can metaphorically sit back and puff on its pipe and think about this thing over here. It's like, why might this have been true? What are the implications of it? And how should I feel about that, and why, and so on. So thinking more deeply and slowly, what Kahneman called thinking slowly versus thinking quickly. Whereas you want machine learning to think quickly, but you want the ability to think deeply, even if it's a little slower. So I'll give you an example of a project we did recently with NIH involving the Cleveland Clinic and a couple other institutions that we ran a project for. And what it did was it took GWAS's genome-wide association studies. Those are sort of big databases of patients that came into a hospital. They got their DNA sequenced because the cost of doing that has gone from infinity to billions of dollars to $100 or so. And so now patients routinely get their DNA sequenced. So you have these big databases of the SNPs, the single nucleotide polymorphisms, the point mutations in a patient's DNA, and the disease that happened to bring them into the hospital. So now you can do correlation studies, machine learning studies of which mutations are associated with and led to which physiological problems and diseases and so on, like getting arthritis and so on. And the problem is that those correlations turn out to be very spurious. They turn out to be very noisy. Very many of them have led doctors onto wild goose chases and so on. And so they wanted a way of eliminating or the bad ones or focusing on the good ones. And so this is where psych comes in, which is psych takes those sort of A to Z correlations between point mutations and the medical condition that needs treatment. And we say, okay, let's use all this public knowledge and common sense knowledge about what reactions occur where in the human body, what polymerizes what catalyzes what reactions, and so on. And let's try to put together a 10 or 20 or 30 step causal explanation of why that mutation might have caused that medical condition. And so psych would put together, in some sense, some Rube Goldberg-like chain that would say, oh yeah, that mutation, if it got expressed, would be this altered protein, which because of that, if it got to this part of the body, would catalyze this reaction. And by the way, that would cause more bioactive vitamin D in the person's blood. And anyway, 10 steps later, that screws up bone resorption. And that's why this person got osteoporosis early in life and so on.
So that's human interpretable, or at least doctor human interpretable.
Exactly.
Yeah.
And the important thing, even more than that, is you shouldn't really trust that 20-step Rube Goldberg chain any more than you trust that initial A to Z correlation, except two things. One, if you can't even think of one causal chain to explain this, then that correlation probably was just noise to begin with. And secondly, and even more powerfully, along the way, that causal chain will make predictions, like the one about having more bioactive vitamin D in your blood. So you can now go back to the data about these patients and say, by the way, did they have slightly elevated levels of bioactive vitamin D in their blood and so on? And if the answer is no, that strongly disconfirms your whole causal chain. And if the answer is yes, that somewhat confirms that causal chain. And so using that, we were able to take this these correlations from this GWAS database, and we were able to essentially focus the researchers' attention on the very small percentage of correlations that had some explanation, and even better, some explanation that also made some independent prediction that they could confirm or disconfirm by looking at the data. So think of it like this kind of synergy where you want the right brain machine learning to quickly come up with possible answers. You want the left brain psych-like AI to think about that and think about why that might have been the case and what else would be the case if that were true and so on, and then suggest things back to the right brain to quickly check out again. So it's that kind of synergy back and forth, which I think is really what's going to lead to general AI, not narrow, brittle machine learning systems, and not just something like psych.
Okay, so that's a brilliant synergy. But I was also thinking in terms of the automated expansion of the knowledge base. You mentioned NLU. This is very early days in the machine learning space of this, but self-supervised learning methods, you have these language models, GPT-3 and so on, that just read the internet and they form representations that can then be mapped to something useful. The question is, what is the useful thing? Like they're now playing with a pretty cool thing called OpenAI Codex, which is generating programs from documentation. Okay, that's kind of useful. It's cool. But my question is, can it be used to generate, in part, maybe with some human supervision, psych-like assertions, help feed psych more assertions from this giant body of internet data?
Yes, that is in fact one of our goals, is how can we harness machine learning? How can we harness natural language processing to increasingly automate the knowledge acquisition process, the growth of psych? And that's what I meant by priming the pump. That, if you sort of learn things at the fringe of what you know already. You learn this new thing is similar to what you know already, and here are the differences and the new things you had to learn about it and so on. So the more you know, the more and more easily you can learn new things. But unfortunately, inversely, if you don't really know anything, then it's really hard to learn anything. And so if you're not careful, if you start out with too small sort of a core to start this process, it never really takes off. And so that's why I view this as a pump priming exercise, to get a big enough manually produced, even though that's kind of ugly duckling technique, put in the elbow grease to produce a large enough core that you will be able to do all the kinds of things you're imagining without sort of ending up with the kind of wacky brittlenesses that we see, for example, in GPT-3, where you'll tell it a story about someone putting poison plotting to poison someone and so on, and then the GPT-3 says, what's the very next sentence? And the next sentence is, oh yeah, that person then drank the poison they just put together. It's like, that's probably not what happened. Or someone, or if you go to Siri and I think I have where can I go for help with my alcohol problem or something, it'll come back and say, I found 7 liquor stores near you,
right?
And so on. So it's one of these things where yes, it may be helpful most of the time. It may even be correct most of the time, but if it doesn't really understand what it's saying, and if it doesn't really understand why things are true, and doesn't really understand how the world works, then some fraction of the time it's going to be wrong. Now, if your only goal is to sort of find relevant information, like search engines do, then being right 90% of the time is fantastic. That's unbelievably great. Okay. However, if your goal is to save the life of your child who has some medical problem, or your goal is to be able to drive, for the next 10,000 hours of driving without getting into a fatal accident and so on, then, error rates down at the 10% level or even the 1% level are not really acceptable.
I like the model of with that learning happens at the edge, and then you kind of think of knowledge as this sphere. So if you want a large sphere because the learning is happening on the surface.
Exactly. So you have the what you can learn next increases quadratically as the diameter of that sphere goes up.
It's nice because you think when you know nothing, it's like you can learn anything, but the reality, not really.
Right. If you know nothing, you can really learn nothing.
Exactly.
You can appear to learn. So I'll also one of the anecdotes I could go back and give you about why I feel so strongly about this personally was in 1980-81. My daughter Nicole was born, and she's actually doing fine now. But when she was a baby, she was diagnosed as having meningitis, and doctors wanted to do all these scary things. And my wife and I were very worried, and we could not get a meaningful answer from her doctors about exactly why they believed this, what the alternatives were, and so on. And fortunately, a friend of mine, Ted Shortliff, was another assistant professor in computer science at Stanford at the time. And he'd been building a program called MISON, which was a medical diagnosis program that happened to specialize in blood infections like meningitis. And so he had privileges at Stanford Hospital because he was also an MD. And so we got hold of her chart and we put in her case, and it came up with exactly the same diagnoses and exactly the same therapy recommendations. But the difference was, because it was a knowledge-based system, a rule-based system, it was able to tell us step by step by step why this was the diagnosis, and step by step why this was the best therapy, the best procedure to do for her, and so on. And there was a real epiphany, because that made all the difference in the world. Instead of blindly having to trust in authority, we were able to understand what was actually going on. And so at that time, I realized that really is what was missing in computer programs, was that even if they got things right, because they didn't really understand the way the world works and why things are the way they are, they weren't able to give explanations of their answer. It's one thing to use a machine learning system that says, this is what you should, I think you should get this operation, and you say why, and it says, 0.83, and you say, no, in more detail, why, and it says 0.831. That's not really very compelling, and that's not really very helpful.
Down. So you're one of the world-class researchers in this space. There's a few groups, like we mentioned, Google and IBM working at this. There's other research labs, but you put also you have an amazing blog. You put
You're
a lot.
Kind.
You paid me to say it. You put a lot of effort sort of to communicating the science of this, and communicating, exposing some of the BS and the sort of the natural, just like in the AI space, the natural charlatanism, if that's a word, in quantum mechanics in general, but quantum computers and so on. Can you give some notes about people or ideas that people like me or listeners in general from outside the field should be cautious of when they're taking in news headings that Google achieved quantum supremacy? So what should we look out for? Where's the charlatans in the space? Where's the BS?
Yeah. So, good question. Unfortunately, quantum computing is a little bit like cryptocurrency or deep learning. Like, there is a core of something that is genuinely revolutionary and exciting. And because of that core, it attracts this sort of vast penumbra of, people making, just utterly ridiculous claims. And so with quantum computing, I mean, I would say that the main way that people go astray is by, not focusing on sort of the question of, are you getting a speed up over a classical computer or not, right? And so people have dismissed quantum supremacy because it's not useful, right? Or, it's not itself, let's say, obviously useful for anything. Okay. But, ironically, these are some of the same people who will go and say, well, we care about useful applications. We care about solving traffic routing and and financial optimization and all these things. And that sounds really good, but their entire spiel is sort of counting on nobody asking the question, yes, but how well could a classical computer do the same thing?
Yes.
Right.
Yeah.
I really mean the entire thing is they say, well, a quantum computer can do this, a quantum computer can do that. Right. And they just avoid the question, are you getting a speed up over a classical computer or not? And, if so, how do you know? Have you really thought carefully about classical algorithms to do, to solve the same problem, right? And a lot of the application areas that, companies and investors are most excited about, that the popular press is most excited about, for quantum computers have been things like machine learning, AI, optimization. Okay. And the problem with that is that since the very beginning, even if you have a perfect, fault tolerant, scalable quantum computer, we have known of only modest speed ups that you can get for these problems. Okay. So there is a famous quantum algorithm called Grover's algorithm. Okay. And what it can do is it can solve many, many of the problems that arise in AI, machine learning, optimization, including NP-complete problems. Okay. But it can solve them in about the square root of the number of steps that a classical computer would need for the same problems. Okay. Now, a square root speed up is, important. It's impressive. It is not an exponential speed up. Okay, so it is not the kind of game changer that, let's say, Shor's algorithm for factoring is, or for that matter, that simulation of quantum mechanics is. Okay, it is a more modest speed up. Let's say, roughly, in theory, it could roughly double the size of the optimization problems that you could handle, right? And so, because people found that, I guess, too boring or too unimpressive, they've gone on to invent all of these heuristic algorithms where, because no one really understands them, you can just project your hopes onto them, right? That, well, maybe it gets an exponential speed up. You can't prove that it doesn't, right. And the burden is on you to prove that it doesn't get a speed up, right? And, so they've done an immense amount of that kind of thing. And a really worrying amount of the case for building a quantum computer has come to rest on this stuff that those of us in this field know perfectly well is on extremely shaky foundations.
So the fundamental question is, show that there's a speed up over the classical.
Absolutely.
And in the space that you're referring to, which is actually really interesting, so the area that a lot of people are excited about is machine learning.
Yeah.
So your sense is, do you think it will... So I know that there's a lot of smoke currently.
Yeah.
But do you think there actually eventually might be breakthroughs where you do get exponential speed ups in the machine learning space?
Absolutely, there might be. I mean, I think we know of modest speed ups that you can get for these problems. I think, whether you can get bigger speed ups is one of the biggest questions for quantum computing theory, for people like me to be thinking about. Now, we had actually recently a really, a super exciting candidate for an exponential quantum speed up for a machine learning problem that people really care about. This is basically the Netflix problem, the problem of recommending products to users given some sparse data about their preferences. Karanitis and Prakash in 2016 had an algorithm for sampling recommendations that was exponentially faster than any known classical algorithm, right? And so, a lot of people were excited. I was excited about it. I had an 18-year-old undergrad by the name of Ewin Tang, and she was, she was obviously brilliant. She was looking for a project. I gave her as a project, can you prove that this speed up is real? Can you prove that, any classical algorithm would need to access exponentially more data, right? And this was a case where if that was true, this was not like a P versus NP type of question, right? This might well have been provable. But she worked on it for a year. She couldn't do it. Eventually, she figured out why she couldn't do it. And the reason was that was false. There is a classical algorithm with a similar performance to the quantum algorithm. So Ewin succeeded in dequantizing that machine learning algorithm. And then in the last couple of years, building on Ewin's breakthrough, a bunch of the other quantum machine learning algorithms that were proposed have now also been dequantized.
Yeah.
Okay.
Well,
and so I would say
kind of an important backward step.
Yes.
Yes. Or a forward step for science, but a step for quantum machine learning.
Yeah.
That precedes the big next forward step.
Right.
If it's possible.
Right. Now, some people will say, well, there's a silver lining in this cloud. They say, well, look, thinking about quantum computing has led to the discovery of potentially useful new classical algorithms.
That's true.
Right. And so, so you get these spin-off applications. But if you want a quantum speed up, you really have to think carefully about that. Ewin's work was a perfect illustration of why. Right. And I think that, the challenge, the field is now open, right? Find a better example. Find, where quantum computers are going to deliver big gains for machine learning. I am, not only do I ardently support, people thinking about that, I'm trying to think about it myself and have my students and postdocs think about it. But we should not pretend that those speed ups are already established. And the problem comes when so many of the companies and journalists in this space are pretending.
I, of course, know theoretically the notion of cancer, but just reading more and more about it, 1.7 million new cancer cases in the United States every year, 600,000 cancer-related deaths every year. So this has a huge impact, United States, globally. When broadly, before we talk about how machine learning, how MIT can help, when do you think we as a civilization will cure cancer? How hard of a problem is it from everything you've learned from it recently?
I cannot really assess it. What I do believe will happen with the advancement in machine learning, that a lot of types of cancer we will be able to predict way early and more effectively utilize existing treatments. I hope at least, that with all the advancements in AI and drug discovery, we would be able to much faster find relevant molecules. What I'm not sure about is how long it will take the medical establishment and regulatory bodies to kind of catch up and to implement it. And I think this is a very big piece of puzzle that is currently not addressed.
That's the really interesting question. So first, a small detail that I think the answer is yes, but is cancer one of the diseases that, when detected earlier, that's a significantly improves the outcomes? Because we'll talk about, there's the cure, and then there is detection. And I think where machine learning can really help is earlier detection. So does detection help
Detection is crucial. For instance, the vast majority of pancreatic cancer patients are detected at the stage that they are incurable. That's why they have such a, terrible survival rate. It's like just few percent over 5 years. It's pretty much today a death sentence. But if you can discover this disease early, there are mechanisms to treat it. And in fact, I know a number of people who were diagnosed and saved just because they had food poisoning. They had terrible food poisoning. They went to ER, they got scanned. There were early signs on the scan, and that's what saved their lives. But this wasn't really an accidental case. So as we become better, we would be able to help to many more people that have, that are likely to develop diseases. And I just want to say that as I got more into this field, I realized that, cancer is, of course, terrible disease, but there are really the whole slew of terrible diseases out there, like neurodegenerative diseases and others. So we, of course, a lot of us are fixated on cancer just because it's so prevalent in our society and you see these people, but there are a lot of patients with neurodegenerative diseases and the kind of aging diseases that we still don't have a good solution for. And and I felt as a computer scientist, we kind of decided that it's other people's job to treat these diseases, because it's like traditionally people in biology or in chemistry or MDs are the ones who are thinking about it. And after kind of start paying attention, I think that it's really a wrong assumption and we all need to join the battle.
So how... It seems like in cancer specifically that there's a lot of ways that machine learning can help. So what's the role of machine learning in the diagnosis of cancer?
So for many cancers today, we really don't know what is your likelihood to get cancer. And for the vast majority of patients, especially on the younger patients, it really comes as a surprise. Like, for instance, for breast cancer, 80% of the patients are first in their families. It's like me. And I never thought that I had any increased risk because, nobody had it in my family. And for some reason in my head, it was kind of inherited disease. But even if I would pay attention, the models that currently, these very simplistic statistical models that are currently used in clinical practice, they really don't give you an answer, so you don't know. And the same true for pancreatic cancer, the same true for non-smoking lung cancer and many others. So what machine learning can do here is utilize all this data to tell us early who is likely to be susceptible, and using all the information that is already there, be it imaging, be it your other tests, and eventually liquid biopsies and others, where the signal itself is not sufficiently strong for human eye to do good discrimination, because the signal may be weak, but by combining many sources, a machine which is trained on large volumes of data can really detect it early. And that's what we've seen with breast cancer, and people are reporting it in other diseases as well.
So you teach a huge machine learning course here at MIT. I could ask you a million questions, but you've seen a lot of students. What ideas do students struggle with the most as they first enter this world of machine learning?
Actually, this year was the first time I started teaching a small machine learning class, and it came as a result of what I saw in my big machine learning class that Tommy Yackel and I built maybe 6 years ago. What we've seen that as this area become more and more popular, more and more people at MIT want to take this class. And while we designed it for computer science majors, there were a lot of people who really are interested to learn it, but unfortunately their background was not enabling them to do well in the class. And many of them associated machine learning with the word struggle and failure, primarily for non-majors. Yeah. And that's why we actually started a new class, which we call Machine Learning from Algorithms to Modeling, which emphasizes more the modeling aspects of it and focuses on, it has majors and non-majors. So we kind of try to extract the relevant parts and make it more accessible, because the fact that we're teaching 20 classifiers in standard machine learning class is really a big question. Do we really need it? But it was interesting to see this from first generation of students, when they came back from their internships and from their jobs, what different and exciting things they can do that I would never think that you can even apply machine learning to. Some of them are like matching, the relations and other things, like variety of different
everything is amenable to machine learning. That actually brings up an interesting point of computer science in general. It almost seems, maybe I'm crazy, but it almost seems like everybody needs to learn how to program these days. If you're 20 years old, or if you're starting school, even if you're an English major, it seems like programming unlocks so much possibility in this world. So when you interacted with those non-majors, is there skills that they were simply lacking at the time that you wish they had, and that they learned in high school and so on? Like, how should education change in this computerized world that we live in?
Because they knew that there is a Python component in the class. Their Python skills were okay, and the class is not really heavy on programming. They primarily kind of add parts to the programs. I think it was more of the mathematical barriers. Mm-hmm. And the class, again, with the design on the majors, was using the notation like big O for complexity, and others. People who come from different backgrounds just don't have it in the lexicon, so necessarily very challenging notion, but they were just not aware. So I think that, kind of linear algebra and probability, the basics, the calculus, multivariate calculus, are things that can help.
What advice would you give to students interested in machine learning, you've talked about detecting, curing cancer, drug design. If they want to get into that field, what should they do? Get into it and succeed as researchers and entrepreneurs.
The first good piece of news is that right now there are lots of resources that are created at different levels, and you can find online or in your school classes which are more mathematical, more applied, and so on. So you can find a kind of a preacher which preaches in your own language, where you can enter the field and you can make many different types of contribution depending of what is your strengths. And the second point, I think it's really important to find some area for which you really care about, and it can motivate your learning. And it can be for somebody curing cancer or doing self-driving cars or whatever, but to find an area where there is data, where you believe there are strong patterns and we should be doing it and we're still not doing it, or you can do it better, and just start there and see where it can bring you.
Let's go into robotics a little bit. What to you is the most beautiful idea in robotics? Whether we're talking about control, or whether we're talking about optimization, the math side of things, or the engineering side of things, or the philosophical side of things.
Mm-hmm. I think I've been lucky to experience something that not so many roboticists have experienced, which is to hang out with some really amazing control theorists. And the clarity of thought that some of the more mathematical control theory can bring to even very complex, messy-looking problems it really had a big impact on me. And I had a day even just a couple of weeks ago where I had spent the day on a Zoom robotics conference, having great conversations with lots of people. Felt really good about the ideas that were flowing and the like. And then I had a late afternoon meeting with one of my favorite control theorists, and we went from these abstract discussions about maybes and what ifs and what a great idea to these super precise statements about systems that aren't that much more simple or abstract than the ones I care about deeply. And the contrast of that is, I don't know, it really gets me. I think people underestimate maybe the power of clear thinking. And so, for instance, deep learning is amazing. I use it heavily in our work. I think it's changed the world, unquestionable. It makes it easy to get things to work without thinking as critically about it. So I think one of the challenges as an educator is to think about how do we make sure people get a taste of the more rigorous thinking that I think goes along with some different approaches.
Yeah, so that's really interesting. So understanding like the fundamentals, the first principles of the problem, where in this case it's mechanics, it's like how a thing moves, how a thing behaves, like all the forces involved, like really getting a deep understanding of that. I mean, from physics, the first principle thing come from physics, and here it's literally physics. Yeah, and this applies in deep learning. This applies to not just, I mean, it applies so cleanly in robotics, but it also applies to just in any data set. I find this true. I mean, driving as well. There's a lot of folks in it that work on autonomous vehicles that don't study driving like deeply. I might be coming a little bit from the psychology side, but I remember I spent a ridiculous number of hours at lunch at this like lawn chair, and I would sit somewhere in MIT's campus. There's a few interesting intersections, and we just watch people cross. So we were studying pedestrian behavior, and I felt like we record a lot of video to try, and then there's the computer vision extracts their movement, how they move their head, and so on. But like every time, I felt like I didn't understand enough. I felt like I wasn't understanding how are people signaling to each other? What are they thinking? How cognizant are they of their fear of death? Like, what's the underlying game theory here? What are the incentives? And then I finally found a live stream of an intersection that's like high def that I would watch so I wouldn't have to sit out there. But that's interesting. So like
That's tough. That's a tough example because, I mean, the learning
humans are involved.
Not just because human, but I think the learning mantra is basically the statistics of the data will tell me things I need to know, right? And for the example you gave of all the nuances of eye contact or hand gestures or whatever that are happening for these subtle interactions between pedestrians and traffic, right? Maybe the data will tell that story. I maybe even one level more meta than what you're saying. For a particular problem, I think it might be the case that data should tell us the story. But I think there's a rigorous thinking that is just an essential skill for a mathematician or an engineer that I just don't want to lose it. There are certainly super rigorous machine learning people. I just think deep learning makes it so easy to do some things that our next generation are not immediately rewarded for going through some of the more rigorous approaches. And then I wonder where that takes us. I'm actually optimistic about it. I just want to do my part to try to steer that rigorous thinking.
So there's like two questions I want to ask. Do you have sort of a good example of rigorous thinking where it's easy to get lazy and not do the rigorous thinking? And the other question I have is like, do you have advice of how to practice rigorous thinking in all the computer science disciplines that we've mentioned?
Yeah, I mean, there are times where problems that can be solved with well-known, mature methods could also be solved with a deep learning approach. And there's an argument that you must use learning even for the parts we already think we know, because if the human has touched it, then you've biased the system and you've suddenly put a bottleneck in there that is your own mental model. But something like inverting a matrix, I think we know how to do that pretty well, even if it's a pretty big matrix, and we understand that pretty well. And you could train a deep network to do it, but you shouldn't, probably.
So in that sense, rigorous thinking is understanding the scope and the limitations of the methods that we have, like how to use the tools of mathematics properly.
Yeah, I think taking a class on analysis is all I'm sort of arguing, right, is to take a chance to stop and force yourself to think rigorously about even the rational numbers or something. It doesn't have to be the end all problem, but that exercise of clear thinking, I think, goes a long way, and I just want to make sure we keep preaching
Don't lose it.
Yeah.
But do you think when you're doing like rigorous thinking, or like maybe trying to write down equations or to sort of explicitly, like formally describe a system, do you think we naturally simplify things too much? Is that a danger you run into? Like in order to be able to understand something about the system mathematically, we make it too much of a toy example.
But I think that's the good stuff, right?
That's how you understand the fundamentals?
I think so. I think maybe even that's a key to intelligence or something. But I mean, okay, what if Newton and Galileo had deep learning? And they had done a bunch of experiments, and they told the world, here's your weights of your neural network. We've solved the problem.
Yeah.
Where would we be today? I don't think we'd be as far as we are. There's something to be said about having the simplest explanation for a phenomenon. So I don't doubt that we can train neural networks to predict even physical, F equals ma type equations. But I want another Newton to come along, because I think there's more to do in terms of coming up with the simple models for more complicated tasks.
Yeah. Let's not offend the AI systems from 50 years from now that are listening to this, that are probably might be better at coming up with F equals ma equations themselves. So
sorry. I actually think learning is probably a route to achieving this. But the representation matters, right? And I think having a function that takes my inputs to outputs that is arbitrarily complex may not be the end goal. I think there's still, the most simple or parsimonious explanation for the data. Simple doesn't mean low dimensional. That's one thing I think that a lesson that we've learned. So, a standard way to do model reduction or system identification and controls is the typical formulation is that you try to find the minimal state dimension realization of a system that hits some error bounds or something like that. And that's maybe not, I think we're learning that state dimension is not the right metric.
Of complexity.
But for me, I think a lot about contact, the mechanics of contact. If a robot hand is picking up an object or something. And when I write down the equations of motion for that, they look incredibly complex, not because, actually not so much because of the dynamics of the hand when it's moving, but it's just the interactions and when they turn on and off, right? So having a high dimensional, but simple description of what's happening out here is fine. But when I actually start touching, if I write down a different dynamical system for every polygon on my robot hand and every polygon on the object, whether it's in contact or not, with all the combinatorics that explodes there, then that's too complex. So I need to somehow summarize that with a more intuitive physics way of thinking. And I'm very optimistic that machine learning will get us there.
What advice would you have for someone new to machine learning? Maybe just started or haven't even started, but are curious about it and who want to get in the field?
Don't be afraid to get your hands dirty. I think that's the main thing. So if something doesn't work, really drill into why things are not working.
Can you elaborate what your hands dirty means?
Right. So for example, if an algorithm, if you try to train a network and it's not converging, whatever, rather than trying to Google the answer or trying to do something, really spend those 5, 8, 10, 15, 20, whatever number of hours really trying to figure it out yourself. Because in that process, you'll actually learn a lot more.
Yeah.
Googling is, of course, like a good way to solve it when you need a quick answer. But I think initially, especially like when you're starting out, it's much nicer to like figure things out by yourself. And I just say that from experience because like when I started out, there were not a lot of resources. So we would like in the lab, a lot of us, like we would look up to senior students. And then the senior students were, of course, busy and they would be like, hey, why don't you go figure it out? Because I just don't have the time. I'm working on my dissertation or whatever. Final year PhD students. And so then we would sit down and like just try to figure it out. And that I think really helped me. That has really helped me figure a lot of things out.
I think in general, if I were to generalize that, I feel like persevering through any kind of struggle on a thing you care about is good.
Yeah.
So you're basically, you try to make it seem like it's good to, spend time debugging, but really any kind of struggle, whatever form that takes. It could be just Googling a lot.
Yeah.
Just basically anything, just sticking with it and going through the hard thing. That could take a form of implementing stuff from scratch. It could take the form of re-implementing with different libraries or different programming languages. It could take a lot of different forms, but struggle is good for the soul.
Yeah. So like in Pittsburgh, where I did my PhD, the thing was it used to snow a lot.
Yeah.
Right. And so when it was snowed, you really couldn't do much. So the thing that a lot of people said was snow builds character because when it's snowing, you can't do anything else. You focus on work.
You've mentioned kind of the YouTube algorithm isn't, E equals MC squared. It's not a single equation. It's potentially sort of more than 1 million lines of code. Sort of, is it more akin to what successful autonomous vehicles today are, which is they're just basically patches on top of patches of heuristics and human experts really tuning the algorithm and have some machine learning modules? Or is it becoming more and more a giant machine learning system with humans just doing a little bit of tweaking here and there? What's your sense? First of all, do you even have a sense of what is the YouTube algorithm at this point? And however much you do have a sense, what does it look like?
Well, we don't usually think about it as the algorithm because it's a bunch of systems that work on different services. The other thing that I think people don't understand is that what you might refer to as the YouTube algorithm from outside of YouTube is actually a bunch of code and machine learning systems and heuristics, but that's married with the behavior of all the people who come to YouTube every day.
So the people are part of the code, essentially.
Exactly, right? Like if there were no people who came to YouTube tomorrow, then the algorithm wouldn't work anymore, right? So that's a critical part of the algorithm. And so when people talk about, well, the algorithm does this, the algorithm does that, it's sometimes hard to understand, well, it could be the viewers are doing that, and the algorithm is mostly just keeping track of what the viewers do and then reacting to those things in sort of more fine-grained situations. And I think that this is the way that the recommendation system and the search system and probably many machine learning systems evolve is, you start trying to solve a problem, and the first way to solve a problem is often with a simple heuristic, right? And you want to say, what are the videos we're going to recommend? Well, how about the most popular ones, right? And that's where you start.
Right.
And over time, you collect some data and you refine your situation so that you're making less heuristics and you're building a system that can actually learn what to do in different situations based on some observations of those situations in the past. And you keep chipping away at these heuristics over time. And so I think that just like with diversity, I think the first diversity measure we took was, okay, not more than 3 videos in a row from the same channel, right? It's a pretty simple heuristic to encourage diversity, but it worked, right? Who needs to see 4, 5, 6 videos in a row from the same channel? And over time, we try to chip away at that and make it more fine-grained and basically have it remove the heuristics in favor of something that can react to individuals and individual situations.
So how do you mentioned, we know that something worked. How do you get a sense when decisions are the kind of A/B testing that this idea was a good one, this was not so good? How do you measure that And across which time scale, across how many users, that kind of thing.
Well, you mentioned that A/B experiments, and so just about every single change we make to YouTube, we do it only after we've run a A/B experiment. And so in those experiments, which run from 1 week to months, we measure literally hundreds of different variables and measure changes with confidence intervals in all of them, because we really are trying to get a sense for ultimately, does this improve the experience for viewers? That's the question we're trying to answer. And an experiment is one way, because we can see certain things go up and down. So for instance, if we noticed in the experiment, people are dismissing videos less frequently, or they're saying that they're more satisfied, they're giving more videos 5 stars after they watch them, then those would be indications of that the experiment is successful, that it's improving the situation for viewers. But we can also look at other things, like we might do user studies where we invite some people in and ask them, like, what do you think about this? What do you think about that? How do you feel about this? And other various kinds of user research. But ultimately, before we launch something, we're going to want to run an experiment so we get a sense for what the impact is going to be, not just to the viewers, but also to the different channels and all of that.
You led the engineering efforts of LinkedIn.
Yep.
And if we look at LinkedIn as a social network,
yep,
and if we look at the Xbox gaming as the social components, the very different kinds of, I imagine, communication going on the two platforms, right? And the line in terms of bullying and so on is different on the two platforms. So how do you, I mean, it's such a fascinating philosophical discussion of where that line is. I don't think anyone knows the right answer. Twitter folks are under fire now, Jack at Twitter, for trying to find that line. Nobody knows what that line is, but how do you try to find the line for, trying to prevent abusive behavior and at the same time let people be playful and joke around and that kind of thing?
I think in a certain way, like, if you have what I would call vertical social networks, it gets to be a little bit easier. So like if you have a clear notion of like what your social network should be used for, or like what you are designing a community around, then you don't have as many dimensions to your sort of content safety problem as as you do in a general purpose platform. I mean, so like on LinkedIn, like the whole social network is about connecting people with opportunity, whether it's helping them find a job or to sort of find mentors, or to sort of help them like find their next sales lead, or to just sort of allow them to broadcast their sort of professional identity to their network of peers and collaborators and sort of professional community. Like that is, I mean, like in some ways, like that's very, very broad, but in other ways it's sort of it's narrow. And so like you can build AIs like machine learning systems that are capable with those boundaries of making better automated decisions about like what is sort of inappropriate and offensive comment or dangerous comment or illegal content when you have some constraints. Same thing with like the gaming social networks, for instance. Like it's about playing games, about having fun, and like the thing that you don't want to have happen on the platform is why bullying is such an important thing. Like bullying is not fun, so you want to do everything in your power to encourage that not to happen. And but I think it's sort of a tough problem in general, and it's one where I think eventually we're going to have some sort of clarification from our policymakers about what it is that we should be doing, like where the lines are, because it's tough. Like like in democracy, right? Like you don't want you want some sort of democratic involvement. Like people should have a say in like where the lines are drawn. Like you don't want a bunch of people making like unilateral decisions. And like we're in a state right now for some of these platforms where you actually do have to make unilateral decisions, where the policy making isn't going to happen fast enough in order to like prevent very bad things from happening. But like we need the policy making side of that to catch up, I think, as quickly as possible, because you want that whole process to be a democratic thing, not a, not some sort of weird thing where you've got a non-representative group of people making decisions that have, like national and global impact.
And it's fascinating because the digital space is different than the physical space in which nations and governments were established. And so what policy looks like globally, what bullying looks like globally, what healthy communication looks like globally is an open question. And we're all figuring it out together. Which is
I mean, with sort of fake news, for instance, and
deep fakes and fake news generated by humans.
Yeah. So we can talk about deep fakes. Like I think that is another sort of very interesting level of complexity. But like if you think about just the written word, right? Yeah. Like we have, we invented papyrus 3,000 years ago, where you could sort of put word on paper, and then 500 years ago, like we get the printing press, like where the word gets a little bit more ubiquitous, and then like you really, really didn't get ubiquitous printed word until the end of the 19th century when the offset press was invented, and then just sort of explodes, and like the cross product of that and the Industrial Revolution's need for educated citizens resulted in like this rapid expansion of literacy and the rapid expansion of the word. But like we had 3,000 years up to that point to figure out like how to, like what's journalism, what's editorial integrity, like what's scientific peer review. And so like you built all of this mechanism to like try to filter through all of the noise that the technology made possible to like, sort of getting to something that society could cope with. And like, if you think about just the PC didn't exist 50 years ago. And so in like this span of, like half a century, like we've gone from no digital, no ubiquitous digital technology to like having a device that sits in your pocket where you can sort of say whatever is on your mind, to like, what did Mary have? And Mary Meeker just released her new like slide deck last week. We've got 50% penetration of the internet to the global population. Like there are like 3.5 billion people who are connected now. So it's like it's crazy, like inconceivable, like how fast all of this happened. So it's not surprising that we haven't figured out what to do yet. But like we gotta really like lean into this set of problems, because like we basically have 3 millennia worth of work to do about how to deal with all of this, and like probably what amounts to the next decade worth of time.
So since we're on the topic of tough, challenging problems, let's look at more on the tooling side in AI that Microsoft is looking at, is face recognition software. So there's a lot of powerful positive use cases for face recognition, but there's some negative ones, and we're seeing those in different governments in the world. So how do you, in terms of advice, I forgot to ask about just machine learning and deep learning for people who are specifically interested in machine learning. How would you recommend they get into the field?
So I would say re-implement everything, and also there is plenty of courses.
So like from scratch?
So on different levels of abstraction in some sense, but I would say re-implement something from scratch, re-implement something from a paper, re-implement something, from podcasts that you have heard about. I would say that's a powerful way to understand things. So it's often the case that you read the description and you think you understand, but you truly understand once you build it. Mm-hmm. Then you actually know what really mattered in the description.
Is there particular topics that you find people just fall in love with? So I tend to really enjoy reinforcement learning because it's much easier to get to a point where you feel like you created something special, like fun games kind of thing.
It's rewarding.
It's rewarding, yeah. As opposed to like re-implementing from scratch, more like supervised learning kind of things. It's yeah.
So, if someone would optimize for things to be rewarding, then it feels that the things that are somewhat generative, they have such a property. Mm-hmm. So you have, for instance, adversarial networks, or you have just even generative language models. Mm-hmm. And you can even see internally, we have seen this thing with our releases. So we released recently 2 models. There is one model called DALL-E that generates images, and there is other model called CLIP that actually you provide various possibilities, what could be the answer to what is on the picture, and it can tell you which one is the most likely. Okay? And in some sense, in case of the first one, DALL-E, it is very easy for you to understand that actually there is magic going on. And in case of the second one, even though it is insanely powerful, and people from vision community, as they started probing it inside, they actually understood how far it goes. It's difficult for person at first to see how well it works. And that's the same as you said, that in case of supervised learning models, you might not kind of see, or it's not that easy for you to understand the strength.
Even though you don't believe in magic, to see the magic.
To see the magic, yeah.
It's a generative. That's really brilliant. So anything that's generative, because then you are at the core of the creation. You get to experience creation without much effort, unless you have to do it from scratch.
And it feels that humans are wired. There is some level of reward for creating stuff.
Yeah.
Like, of course, different people have a different weight on this reward.
Yeah. In the big objective function.
In the big objective function of a person.
Of a person. So maybe an extension of that, there has been a resurgence in computer science and machine learning and neural networks. So using data to construct algorithms. So it's another way to construct algorithms, really.
Yes, exactly.
If you can think of it that way. So as opposed to natural language to construct algorithms, use data to construct algorithms. So what's your view of this branch of computer science, where data is almost more important than the mechanism of the algorithm?
It seems to be suited to a certain kind of non-geek, and which is probably why it's taken off. That it has its own community that really resonates with that. But it's hard to trust something like that, because nobody, even the people who work with it, that they have no idea what has been learned.
That's a really interesting thought, that it makes algorithms more accessible to a different community, a different type of brain.
Yep.
And that's really interesting, because just like literate programming perhaps could make programming more accessible to a certain kind of brain.
There are people who think it's just a matter of education, and anybody can learn to be a great programmer. Anybody can learn to be a great skier. I wish that were true, but I know that there's a lot of things that I've tried to do, and I was well motivated, and I kept trying to build myself up, and I never got past a certain level. I can't view, for example, three-dimensional objects in my head. I have to make a model and look at it and study it from all points of view, and then I start to get some idea of. But other people are good at 4 dimensions. I mean,
physicists.
Yeah.
So incredible. So this self-play of quarks, taking back to the beginning of our conversation a little bit, there's so many exciting possibilities about artificial intelligence understanding the basic laws of physics. Do you think AI will help us unlock? There's been quite a bit of excitement throughout the history of physics of coming up with more and more general, simple laws that explain the nature of our reality. And then the ultimate of that would be a theory of everything that combines everything together. Do you think it's possible that, well, we humans, but perhaps AI systems will figure out a theory of physics that unifies all the laws of physics?
Yeah, I think it's absolutely possible. I think it's very clear that we're going to see a great boost to science. We're already seeing a boost actually from machine learning helping science. AlphaFold was an example, the decades-old protein folding problem solved, and gradually, yeah, unless we go extinct by doing something dumb like we discussed, I think it's very likely that our understanding of physics will become so good that our technology will no longer be limited by human intelligence, but instead be limited by the laws of physics. So our tech today is limited by what we've been able to invent, right? I think as AI progresses, it'll just be limited by the speed of light and other physical limits, which will mean it's going to be just dramatically beyond, where we are now.
Do you think it's a fundamentally mathematical pursuit of trying to understand like the laws of that govern our universe from a mathematical perspective? So almost like if it's AI, it's exploring the space of like theorems and those kinds of things, or is there some other is there some other more computational ideas, more sort of empirical ideas?
They're both, I would say. It's really interesting to look out at the landscape of everything we call science today. So here you come now with this big new hammer. It says machine learning on it, and ask, where are there some nails that you can help with here that you can hammer? Ultimately, if machine learning gets to the point that it can do everything better than us, it will be able to help across the whole space of science. But maybe we can anchor it by starting a little bit right now near term and see how we kind of move forward. So like right now, first of all, you have a lot of big data science, right, where, for example, with telescopes, we are able to collect way more data every hour than a grad student can just pour over like in the old times, right? Mm-hmm. And machine learning is already being used very effectively, even at MIT, right, to find planets around other stars, to detect exciting new signatures of new particle physics in the sky, and to detect the ripples in the fabric of space-time that we call gravitational waves caused by enormous black holes crashing into each other halfway across our observable universe. Machine learning is running and ticking right now, doing all these things, and it's really helping all these experimental fields. There is a separate front of physics, computational physics, which is getting an enormous boost also. So we had to do all our computations by hand, right? People would have these giant books with tables of logarithms, and oh my God, it pains me to even think how long time it would have taken to do simple stuff. Then we started to get little calculators and computers that could do some basic math for us. Now, what we're starting to see is kind of a shift from GoFi computational physics to neural network computational physics. What I mean by that is most computational physics would be done by humans programming in the intelligence of how to do the computation into the computer. Just as when Garry Kasparov got his posterior kicked by IBM's Deep Blue in chess, humans had programmed in exactly how to play chess. Yes. Intelligence came from the humans. It wasn't learned, right? Mu0 can be not only Kasparov in chess, but also Stockfish, which is the best sort of GoFi chess program, by learning. And we're seeing more of that now, that shift beginning to happen in physics. So let me give you an example. So lattice QCD is an area of physics whose goal is basically to take the periodic table and just compute the whole thing from first principles. Mm-hmm. This is not the search for a theory of everything. We already know the theory that's supposed to produce as output the periodic table, which atoms are stable, how heavy they are, all that good stuff. Their spectral lines. It's a theory, lattice QCD. You can put it on your T-shirt. Our colleague Frank Wilczek got the Nobel Prize for working on it. But the math is just too hard for us to solve. We have not been able to start with these equations and solve them to the extent that we can predict, oh yeah, and then there is carbon, and this is what the spectrum of the carbon atom looks like. But awesome people are building these supercomputer simulations where you just put in these equations and you make a big cubic lattice of space, or actually it's a very small lattice because you're going at the subatomic scale, down to the subatomic scale, and you try to solve this. But it's just so computationally expensive that we still haven't been able to calculate things as accurately as we measure them in many cases. And now machine learning is really revolutionizing this. So my colleague Fiona Shanahan at MIT, for example, she's been using this really cool machine learning technique called normalizing flows, where she's realized she can actually speed up the calculation dramatically by having the AI learn how to do things faster. Another area like this where we suck up an enormous amount of supercomputer time to do physics is black hole collisions. So now that we've done the sexy stuff of detecting a bunch of this with LIGO and other experiments, we want to be able to know what we're seeing. And so it's a very simple conceptual problem. It's the two-body problem. Newton solved it for classical gravity hundreds of years ago, but the two-body problem is still not fully solved
for black holes.
In Einstein's gravity, because they won't just orbit each other forever anymore. Two things: they give off gravitational waves, and eventually they crash into each other. And the game, what you want to do is you want to figure out, okay, what kind of wave comes out as a function of the masses of the two black holes, as a function of how they're spinning relative to each other, etc. And that is so hard. It can take months of supercomputer time on massive numbers of cores to do it. Wouldn't it be great if you can use machine learning to greatly speed that up, right? Now you can use the expensive old GoFi calculation as the truth, and then see if machine learning can figure out a smarter, faster way of getting the right answer. Yet another area like computational physics. These are probably the big three that suck up the most computer time: lattice QCD, black hole collisions, and cosmological simulations, where you take not a subatomic thing and try to figure out the mass of the proton, but you take something with it's enormous and try to look at how all the galaxies get formed in there.
Oh, wow. Yeah.
There again, there are a lot of very cool ideas right now about how you can use machine learning to do this sort of stuff better. The difference between this and the big data is you kind of make the data yourself, right? So, and then finally, we're looking over the physics landscape and seeing what can we hammer with machine learning, right? So we talked about experimental data, big data, discovering cool stuff that we humans then look more closely at. Then we talked about taking the expensive computations we're doing now and figuring out how to do them much faster and better with AI. And finally, let's go really theoretical. So things like discovering equations, having deep fundamental insights. This is something closest to what I've been doing in my group. We talked earlier about the whole AI Feynman project, where if you just have some data, how do you automatically discover equations that seem to describe this well, that you can then go back as a human and work with and test and explore? And you asked a really good question also about if this is sort of a search problem in some sense. That's very deep, actually, what you said, because it is. Suppose I ask you to prove some mathematical theorem. What is a proof in math? It's just a long string of steps, logical steps that you can write out with symbols. And once you find it, it's very easy to write a program to check whether it's a valid proof or not. So why is it so hard to prove it then? Well, because there are ridiculously many possible candidate proofs you could write down, right? If the proof contains 10,000 symbols, even if there were only 10 options for what each symbol could be, that's 10 to the power 1,000 possible proofs, which is way more than there are atoms in our universe, right? So you could say it's trivial to prove these things. You just write a computer, generate all strings, and then check, is this a valid proof? No. Is this a valid proof? No. And then You just keep doing this forever. But there are but it is fundamentally a search problem. You just want to search the space of all strings of symbols to find one that is the proof, right? Mm-hmm. And there's a whole area of machine learning called search. How do you search through some giant space to find the needle in the haystack? Mm-hmm. It's easier in cases where there's a clear measure of good, like you're not just right or wrong, but this is better and this is worse. So you can maybe get some hints as to which direction to go in. That's why we talked about neural networks work so well.
Mm-hmm. But let me ask nevertheless about applications to machine learning.
Okay.
So if you look at the scale of 5, 10, 20 years, is it possible to, before we understand the nature of human intelligence and general intelligence, do you think we'll start falling out of this exploration of neuromorphic systems' ability to solve some of the problems that the machine learning systems of today can't solve?
I'm really hesitant to overpromise, right. So I really don't know. I don't really understand machine learning in a lot of senses. I mean, machine learning, from my perspective, appears to require that you know precisely what your input is and also what your goal is. You usually have some objective function or something like that, and that's very limiting. I mean, of course, a lot of times that's the case. You know, there's a picture and there's a horse in it, so you're done. But that's not a very interesting problem. I think when I think about intelligence, it's almost defined by the ability to handle problems where you don't know what your inputs are going to be, and you don't even necessarily know what you're trying to accomplish. I mean, I'm not sure what I'm trying to accomplish in this world, but
at all scales.
Yeah, at all scales, right? I mean, I'm more drawn to the underlying phenomena, the critical dynamics of this system, trying to understand how elements that you build into your hardware result in emergent, fascinating activity that was very difficult to predict. Things like that. So, but I got to be really careful, because I think a lot of other people who, if they found themselves working on this project in my shoes, they would say, all right, what are all the different ways we can use this for machine learning? Actually, let me just definitely mention a colleague at NIST, Mike Schneider. He's also very much interested, particularly in the superconducting side of things, using the incredible speed, power efficiency. Also Ken Segal at Colgate, other people working on specifically the superconducting side of this for machine learning and deep feed-forward neural networks. There, the advantages are obvious. It's extremely fast.
Yeah, so that's less on the nature of intelligence and more on various characteristics of this hardware that you can use for the basic computation as we know it today.
Yeah,
and communication.
One of the things that Mike Schneider's working on right now is an image classifier at a relatively small scale. I think he's targeting that 9-pixel problem where you can have 3 different characters and you put in a 9-pixel image and you classify it as one of these three categories. And that's going to be really interesting to see what happens there, because if you can show that even at that scale, you just put these images in and you get it out, and he thinks he can do it. I forgot if it's a nanosecond or some extremely fast classification time. It's probably less. It's probably 100 picoseconds or something. There you have challenges though, because the Josephson junctions themselves, the electronic circuit, is extremely power efficient, some orders of magnitude for something more than a transistor doing the same thing. But when you have to cool it down to 4 Kelvin, you pay a huge overhead just for keeping it cold, even if it's not doing anything. So it has to work at large scale in order to overcome that power penalty. But that's possible. It's going to have to get that performance. And this is sort of what you were asking about before, is like, how much better than silicon would it need to be? And the answer is, I don't know. I think if it's just overall better than silicon at a problem that a lot of people care about, maybe it's image classification, maybe it's face recognition, maybe it's monitoring credit transactions, I don't know, then I think it will have a place. It's not going to be in your cell phone, but it could be in your data center.
So what about in terms of the data center, I don't know if you're paying attention to the various systems, like Tesla recently announced Dojo, which is a large-scale machine learning training system. That, again, the bottleneck there is probably going to be communication between those systems. Is there something from your work on everything we've been talking about in terms of superconductive hardware that could be useful there?
Tomorrow, no. In the long term, it could be the whole thing. It could be nothing. I don't know, but definitely, when you look at so I don't know that much about Dojo. My understanding is that's new, right? That's just coming online.
Well, I don't even know where it hasn't come online. Okay. And when you announce big sexy, so let me explain to you the way things work in
in the world out there.
In the world of business and marketing, it's not always clear where you are on the coming online part of that. So I don't know where they are exactly, but the vision is from ground up to build a very, very large scale modular machine learning ASIC, basically hardware that's optimized for training neural networks. And of course, there's a lot of companies that are small and big working on this kind of problem. The question is how to do it in a modular way that has very fast communication. The interesting aspect of Tesla is you have a company that, at least at this time, is so singularly focused on solving a particular machine learning problem, and is making obviously a lot of money doing so, because the machine learning problem happens to be involved with autonomous driving. Right. And so you have a system that's driven by an application. And that's really interesting because, you have maybe Google working on TPUs and so on. You have all these other companies with ASICs. They're usually more kind of always thinking general. So I like it when it's driven by a particular application, because then you can really get to it's somehow, if you just talk broadly about intelligence, you may not always get to the right solutions. It's nice to couple that sometimes with specific, clear illustration of something that requires general intelligence, which for me, driving is one such case.
I think you're exactly right. Sometimes just having that focus on that application brings a lot of people, focuses their energy and attention. I think that, so one of the things that's appealing about what you're saying is not just that the application is specific, but also that the scale is big, and that the benefit is also huge. So
financial and to humanity.
Right. Yeah. So I guess let me just try to understand, is the point of this Dojo system to figure out the parameters that then plug into neural networks, and then you don't need to retrain, you just make copies of a certain chip that has all the parameters established? Or
no, it's straight up retraining a large neural network over and over and over.
So you have to do it once for every new car?
No, you have to. So they do this interesting process, which I think is a process for machine learning, supervised machine learning systems. You're going to have to do, which is you have a system, you train your network once. It takes a long time. I don't know how long, but maybe a week to train. And then you deploy it on, let's say, about 1 million cars. I don't know what the number is.
But that part, you just write software that updates some weights in a table and
But there's a loop back.
Okay.
Each of those cars run into trouble rarely, but like they catch the edge cases of the performance of that particular system, and then send that data back. And either automatically or by humans, that weird edge case data is annotated, and then the network has to become smart enough to now be able to perform in those edge cases, so it has to get retrained. There's clever ways of retraining different parts of that network, but for the most part, I think they prefer to retrain the entire thing. So you have this giant monster that kind of has to be retrained regularly. I think the vision with Dojo is to have a very large machine learning focused, driving focused supercomputer that then is sufficiently modular that could be scaled to other machine learning applications. But like So they're not limiting themselves completely to this particular application, but this application is the way they kind of test this iterative process of machine learning. Is you make a system that's very dumb, deploy it, get the edge cases where it fails, make it a little smarter, it becomes a little less dumb, and that through that iterative process achieves something that you can call intelligent or is smart enough to be able to solve this particular application. So it has to do with training neural networks fast and training neural networks that are large.
But also based on an extraordinary amount of diverse input.
Data, yeah.
And that's one of the things. So this does seem like one of those spaces where the scale of superconducting optoelectronics, the way that, so when you talk about the weaknesses, like I said, okay, well, you have to cool it down. At this scale, that's fine. Because that's not too much of an added cost. Most of your power is being dissipated by the circuits themselves, not the cooling. And also, you have one centralized kind of cognitive hub, if you will. And so if we're talking about putting a superconducting system in a car, that's questionable. Do you really want a cryostat in the trunk of every one of your car? It'll fit. It's not that big of a deal, but hopefully there's a better way, right? But since this is sort of a central supreme intelligence or something like that, and it needs to really have this massive data acquisition, massive data integration, I would think that that's where large-scale spiking neural networks with vast communication and all these things would have something pretty tremendous to offer. It's not going to happen tomorrow. There's a lot of development that needs to be done. But, we have to be patient with self-driving cars for a lot of reasons. We were all optimistic that they would be here by now. And okay, they are to some extent. But if we're thinking 5 or 10 years down the line, it's not unreasonable. One other thing let me just mention, getting into self-driving cars and technologies that are using AI out in the world, this is something NIST cares a lot about. Elham Tabasi is leading up a much larger effort in AI at NIST than my little project. And really central to that mission is this concept of trustworthiness. Mm-hmm. So when you're going to deploy this neural network in every single automobile with so much on the line, you have to be able to trust that. So now how do we know that we can trust that? How do we know that we can trust the self-driving car or the supercomputer that trained it? There's a lot of work there, and there's a lot of that going on at NIST, and it's still early days. I mean, you're familiar with the black box problem and all that.
But there's a fascinating dance in engineering with like safety critical systems. There's a desire in computer science. I just recently talked to Don Knuth to for algorithms and for systems, for them to be provably correct or provably safe. And this is one other difference between humans and biological systems is we're not provably anything.
Right.
And so there's some aspect of imperfection.
Yes.
That we need to have built in, like robustness to imperfection, be part of our systems, which is a difficult thing for engineers to contend with. They're very uncomfortable with the idea that you have to be okay with failure and almost engineer failure into the system.
Mathematicians hate it too. But I think it was Turing who said something along the lines of, I can give you an intelligent system or I can give you a flawless system, but I can't give you both. And it's in sort of creativity and abstract thinking seem to rely somewhat on stochasticity and not having components that perform exactly the same way every time.
This is where like the disagreement I have with, not disagreement, but a different view on the world. I'm with Turing. When I talk to robot colleagues, that sounds like I'm talking to robots, colleagues that are roboticists, the goal is perfection. And to me is like, no, I think the goal should be imperfection that's communicated. And through the interaction between humans and robots, that imperfection becomes a feature, not a bug.
Right.
Like together, seen as a system, the human and the robot together are better than either of them individually. Mm-hmm. But the robot itself is not perfect in any way. Of course, there's had a bunch of disagreements, including with Mr. Elon about. To me, autonomous driving is fundamentally a human-robot interaction problem, not a robotics problem. Okay. To Elon, it's a robotics problem. That's actually an open and fascinating question, whether humans can be removed from the loop completely. Recently, there are a few hackers who tricked autopilot to act in unexpected ways with adversarial examples. So we all know that neural network systems are very sensitive to minor disturbances to these adversarial examples on input. Do you think it's possible to defend against something like this for the broader, for the industry?
Sure.
So,
yeah.
Can you elaborate on the confidence behind that answer?
Well, a neural net is just like basically a bunch of matrix math. I mean, you have to be like a very sophisticated, somebody who really understands neural nets and like basically reverse engineer how the matrix is being built and then create a little thing that's just exactly causes the matrix math to be slightly off. But it's very easy to then block that by having basically negative recognition. It's like if the system sees something that looks like a matrix hack, exclude it. It's such an easy thing to do.
So learn both on the valid data and the invalid data. So basically learn on the adversarial examples to be able to exclude them.
Yeah, you basically want to both know what is a car and what is definitely not a car. And you train for this is a car and this is definitely not a car. Those are two different things. People have no idea neural nets really. They probably think neural nets involves fishing net or something.
Over time.
On the topic of adaptive modeling, and you talk about lifelong learning, which is I think a topic that's understudied, or maybe because nobody knows what to do with it. But if you look at Alexa or most of our artificial intelligence systems that are primarily machine learning based systems or dialogue systems, all those kinds of things, they know very little about you in the sense of the lifelong learning sense that we learn as humans, we learn a lot about each other, not in the quantity of facts, but like the temporally rich set of information that seems to pick up the crumbs along the way that somehow seems to capture a person pretty well. Do you have any ideas how to do lifelong learning? Because it seems like most of the machine learning community does not.
No. Well, by the way, not only does the machine learning community not spend a lot of time on lifelong learning, I don't think they spend a lot of time on learning, period, in the sense that they tend to be very task focused. Everybody is overfitting to whatever problem is they happen to have. They're over-engineering their solutions to the task. Even the people, and I think these people too, are trying to solve a hard problem of transfer learning, right? I'm going to learn on one task, I'm going to learn the other task. You still end up creating the task. It's like looking for your keys where the light is, because that's where the light is, right? It's not because the keys have to be there. I mean, and one could argue that we tend to do this in general. We tend to kind of do it as a group. We tend to hill climb and get stuck in local optima. And I think we do this in the small as well. I think it's very hard to do because look, here's the hard thing about AI, right? The hard thing about AI is it keeps changing on us, right? What is AI? AI is the art and science of making computers act the way they do in the movies, right? That's what it is, right?
That's a good definition.
But beyond that,
and they keep coming up with new movies.
Yes, and it's just right, exactly. We are driven by this kind of need to the sort of ineffable quality of who we are, which means that the moment you understand something is no longer AI, right? Well, we understand this. That's just, you take the derivative and you divide by 2 and then you average it out over time in the window. So therefore, that's no longer AI. So the problem is unsolvable because it keeps kind of going away. This creates a kind of illusion, which I don't think is an entire illusion, of either there's very simple task-based things you can do very well and over-engineer. There's all of AI, and there's nothing in the middle. It's very hard to get from here to here, and it's very hard to see how to get from here to here. And I don't think that we've done a very good job of it because we get stuck trying to solve the small problem that's in front of it, myself included. I'm not going to pretend that I'm better at this than anyone else. And of course, all the incentives in academia and in industry are set to make that very hard because you have to get the next paper out, you have to get the next product out, you have to solve this problem, and it's very sort of naturally incremental. And none of the incentives are set up to allow you to take a huge risk unless you're already so well established you can take that big risk. And if you're that well established that you can take that big risk, then you've probably spent much of your career taking these little risks, relatively speaking. And so you have got a lifetime of experience telling you not to take that particular big risk, right? So the whole system's set up to make progress very slow. That's fine. It's just the way it is. But it does make this gap seem really big, which is my long way of saying I don't have a great answer to it, except that stop doing n equals 1. At least try to get n equal 2 and maybe n equals 7 so that you can say, I'm going to, or maybe t is a better variable here. I'm going to not just solve this problem, I'm going to solve this problem and another problem. I'm not going to learn just on you. I'm going to keep living out there in the world and just seeing what happens, and that we'll learn something as designers, and our machine learning algorithms and our AI algorithms can learn as well. But unless you're willing to build a system which you're going to have live for months at a time in an environment that is messy and chaotic, you cannot control, then you're never going to make progress in that direction. So I guess my answer to you is yes. My idea is that you should, it's not no, it's yes, you should be deploying these things and making them live for months at a time and be okay with the fact that it's going to take you 5 years to do this. Not rerunning the same experiment over and over again and refining the machine so it's slightly better at whatever, but actually having it out there and living in the chaos of the world and seeing what its learning algorithm, say, can learn, what data structure it can build and how it can go from there. Without that, you're going to be stuck ultimately.
What do you think about the possibility of n equals 1 growing? Is a probably crude approximation, but growing, like if we look at language models like GPT-3, if you just make it big enough, it'll swallow the world. Meaning like it'll solve all your t to infinity by just growing in size. Of this, taking the small over-engineered solution and just pumping it full of steroids in terms of compute, in terms of size of training data, and the Yann LeCun style self-supervised or the OpenAI self-supervised, just throw all of YouTube at it and it will learn how to reason, how to paint, how to create music, how to love, all of that by watching YouTube videos.
I mean, I can't think of a more terrifying world to live in than a world that is based on YouTube videos. But yeah, I think the answer that I just kind of don't think that'll quite, well, it won't work that easily, right? You will get somewhere and you will learn something, which means it's probably worth it, but you won't get there. You won't solve here's the thing. We build these things and we say we want them to learn, but what actually happens, and let's say they do learn, I mean, certainly every paper I've gotten published, the things learn. I don't know about anyone else. But they actually change us, right? We react to it differently, right? So we keep redefining what it means to be successful, both in the negative in the AI case, but also in the positive in that, oh, well, this is an accomplishment. I'll give you an example, which is like the one you just described with GPT. Let's get completely out of machine learning. Well, not completely, but mostly out of machine learning. Think about Google. People were trying to solve information retrieval, the ad hoc information retrieval problem forever. I mean, first major book I ever read about it was 71, I think was when it came out. Anyway, it's, we'll treat everything as a vector and we'll do these vector space models and whatever. And that was all great. And we made very little progress. I mean, we made some progress. And then Google comes and makes the ad hoc problem seem pretty easy. I mean, it's not. There's lots of computers and databases involved, but, and there's some brilliant algorithmic stuff behind it too. And some systems building. But the problem changed, right? If you've got a world that's that connected so that you have, there are 10 million answers, quite literally, to the question that you're asking, then the problem wasn't give me the things that are relevant. The problem is don't give me anything that's irrelevant, at least in the first page, because nothing else matters. So Google is not solving the information retrieval problem, at least not on this webpage. Google is minimizing false positives, which is not the same thing as getting an answer. It turns out it's good enough for what it is we want to use Google for, but it also changes what the problem was we thought we were trying to solve in the first place. You thought you were trying to find an answer, but you're not, or you're trying to find the answer, but it turns out you're just trying to find an answer. Now, yes, it is true, it's also very good at finding you exactly that web page. Of course, you trained yourself to figure out what the keywords were to get you that web page. But in the end, by having that much data, you've just changed the problem into something else. You haven't actually learned what you set out to learn. Now, the counter to that would be maybe we're not doing that either. We just think we are because we're in our own heads. Maybe we're learning the wrong problem in the first place. But I don't think that matters. I think the point is that Google has not solved information retrieval. Google has done amazing service. I have nothing bad to say about what they've done. Lord knows my entire life is better because Google exists. And if it weren't for Google Maps, I don't think I would have ever found this place.
Where is this?
Like 95. I see 110 and I see, but where did 95 go? So I'm very grateful for Google. But, they just have to make certain the first 5 things are right.
Yeah.
And everything after
good enough.
But what do you think the future of programming looks like? What do you hope the future of programming looks like if we zoom in on the computational fields, on data science, on machine learning?
I hope Swift is successful because the goal of Swift, the way Chris Lattner describes it, is to be infinitely hackable. And that's what I want. I want something where me and the people I do research with and my students can look at and change everything from top to bottom. There's nothing mysterious and magical and inaccessible. Unfortunately, with Python, it's the opposite of that because Python's so slow. It's extremely unhackable. You get to a point where it's like, okay, from here on down it's C. So your debugger doesn't work in the same way. Your profiler doesn't work in the same way. Your build system doesn't work in the same way. It's really not very hackable at all.
What's the part you would like to be hackable? Is it for the objective of optimizing training of neural networks, inference of neural networks? Is it performance of the system? Or is there some non-performance related, just
it's everything.
Ideas?
I mean, in the end, I want to be productive as a practitioner. So that means that, like at the moment, our understanding of deep learning is incredibly primitive. There's very little we understand. Most things don't work very well, even though it works better than anything else out there.
Right.
There's so many opportunities to make it better. So you look at any domain area, like, speech recognition with deep learning or natural language processing classification with deep learning or whatever. Every time I look at an area with deep learning, I always see like, oh, it's terrible. There's lots and lots of obviously stupid ways to do things that need to be fixed. So then I want to be able to jump in there and quickly experiment and make them better.
You think the programming language is has a role in that?
Huge role, yeah. So currently, Python has a big gap in terms of our ability to innovate, particularly around recurrent neural networks and natural language processing, because it's so slow. The actual loop where we actually loop through words, we have to do that whole thing in CUDA C. Mm-hmm. So we actually can't innovate with the kernel, the heart of that most important algorithm. Mm-hmm. And it's just a huge problem. And this happens all over the place. So we hit, research limitations. Another example, convolutional neural networks, which are actually the most popular architecture for lots of things, maybe most things in deep learning. We almost certainly should be using sparse convolutional neural networks, but only like 2 people are, because to do it, you have to rewrite all of that CUDA C level stuff. And just researchers and practitioners don't. So like there's just big gaps in like what people actually research on, what people actually implement because of the programming language problem.
So you think it's just too difficult to write in CUDA C, that a higher level programming language like Swift should enable the easier fooling around creative stuff with RNNs or with sparse convolutional neural networks?
Kind of.
Who's at fault? Who's in charge of making it easy for a researcher to play around?
I mean, no one's at fault. It's just nobody's got around to it yet, it's hard, right? And I mean, part of the fault is that we ignored that whole APL kind of direction. Nearly everybody did for 60 years, 50 years. But recently, people have been starting to reinvent pieces of that and kind of create some interesting new directions in the compiler technology. So the place where that's particularly happening right now is something called MLIR, which is something that, again, Chris Lattner, the Swift guy, is leading. And because it's actually not going to be Swift on its own that solves this problem. Mm-hmm. Because the problem is that currently writing a acceptably fast, GPU program is too complicated, regardless of what language you use.
Right.
And that's just because if you have to deal with the fact that I've got, 10,000 threads and I have to synchronize between them all and I have to put my thing into grid blocks and think about warps and all this stuff, it's just so much boilerplate that to do that well, you have to be a specialist at that, and it's going to be a year's work to, optimize that algorithm in that way. But with things like tensor comprehensions and tile and MLIR and TVM, there's all these various projects which are all about saying, let's let people create like domain-specific languages for tensor computations. These are the kinds of things we do generally on the GPU for deep learning, and then have a compiler which can optimize that tensor computation. A lot of this work is actually sitting on top of a project called Halide, which is a mind-blowing project where they came up with such a domain-specific language. In fact, two. One domain-specific language for expressing this is what my tensor computation is, and another domain-specific language for expressing this is the kind of the way I want you to structure the compilation of that, like do it block by block and do these bits in parallel.
Mm-hmm.
And they were able to show how you can compress the amount of code by 10x compared to optimized GPU code and get the same performance. So that's so these other things are kind of sitting on top of that kind of research, and MLIR is pulling a lot of those best practices together. And now we're starting to see work done on making all of that directly accessible through Swift, so that I could use Swift to kind of write those domain-specific languages. And hopefully we'll get then Swift CUDA kernels written in a very expressive and concise way that looks a bit like J and APL, and then Swift layers on top of that, and then a Swift UI on top of that. And, it'll be so nice if we can get to that point.
Now, does it all eventually boil down to CUDA and NVIDIA GPUs?
Unfortunately, at the moment it does. But one of the nice things about MLIR, if AMD ever gets their act together, which they probably won't, is that they or others could write MLIR backends for other GPUs or other tensor computation devices, of which today there are an increasing number, like GraphCore or Vertex AI or whatever. So, yeah, being able to target lots of backends would be another benefit of this, and the market really needs competition because at the moment NVIDIA is massively overcharging for their kind of enterprise class cards because there is no serious competition because nobody else is doing the software properly.
In the cloud, there is some competition, right? But
not really, other than TPUs perhaps.
TPUs,
but TPUs are almost unprogrammable at the moment.
So you can't. The TPUs has the same problem that you can't.
It's even worse. So TPUs, Google actually made an explicit decision to make them almost entirely unprogrammable because they felt that there was too much IP in there, and if they gave people direct access to program them, people would learn their secrets.
Yeah.
So you can't actually directly program the memory in a TPU. You can't even directly create code that runs on and that you look at on the machine that has the GPU. It all goes through a virtual machine. So all you can really do is this kind of cookie cutter thing of plug in high level stuff together, which is just super tedious and annoying and totally unnecessary.
So what was the... So there's a lot of excitement and progress in the field of machine learning.
Yes.
And reinforcement learning and the neural network variant of that with deep reinforcement learning. Do you see a role of machine learning in... So a lot of the success with flying robots did not rely on machine learning, except for maybe a little bit of the perception, the computer vision side. On the control side and the planning, do you see there's a role in the future for machine learning?
So let me disagree a little bit with you. I think we never perhaps called out learning, but even this very simple idea of being able to fly through a constrained space. The first time you try it, you might get it wrong if the task is challenging. And the reason is, to get it perfectly right, you have to model everything in the environment.
Right.
And flying is notoriously hard to model. there are aerodynamic effects that we constantly discover. Even just before I was talking to you, I was talking to a student about how blades flap when they fly.
Wow.
And that ends up changing how a rotorcraft is accelerated in the angular direction.
There's these like micro flaps or something.
It's not micro flaps. So we assume that each blade is rigid, but actually it flaps a little bit.
Oh.
It bends.
Interesting, yeah.
And so the models rely on the fact, on an assumption that they're actually rigid. But that's not true. If you're flying really quickly, these effects become significant. If you're flying close to the ground, you get pushed off by the ground, right? Something which every pilot knows when he tries to land or she tries to land. This is called a ground effect. Something very few pilots think about is what happens when you go close to a ceiling. Well, you get sucked into a ceiling. There are very few aircrafts that fly close to any kind of ceiling. Likewise, when you go close to a wall, there are these wall effects. And if you've gone on a train and you pass another train that's traveling in the opposite direction, you feel the buffeting. And so these kinds of microclimates affect our UAVs significantly.
And they're impossible to model, essentially.
I wouldn't say they're impossible to model, but the level of sophistication you would need in the model and the software would be tremendous. Plus, to get everything right would be awfully tedious. So the way we do this is over time, we figure out how to adapt to these conditions. So early on, we used a form of learning that we call iterative learning. So this idea, if you want to perform a task, there are a few things that you need to change and iterate over a few parameters that over time you can figure out. So I could call it policy gradient reinforcement learning, but actually it was just iterative learning.
Iterative learning.
And so this was there way back. I think what's interesting is if you look at autonomous vehicles today, learning could occur in two pieces. One is perception, understanding the world. Second is action, taking actions. Everything that I've seen that is successful is on the perception side of things. So in computer vision, we've made amazing strides in the last 10 years. So recognizing objects, actually detecting objects, classifying them, and tagging them in some sense, annotating them. This is all done through machine learning. On the action side, on the other hand, I don't know of any examples where there are fielded systems where we actually learn the right behavior.
Outside of single demonstration of successfully,
in the laboratory, this is the holy grail. Can you do end-to-end learning? Can you go from pixels to motor currents? This is really, really hard. And I think if you go forward, the right way to think about these things is data-driven approaches, learning-based approaches, in concert with model-based approaches, which is the traditional way of doing things.
Right.
So I think there's a role for each of these methodologies.
So what do you think?
70% of our time on core business, 20% on adjacent business, and 10% on other. And he proved mathematically, of course, he's a brilliant mathematician, that you needed that 10%, right, to make the sum of the growth work. And it turns out he was right.
So getting into the world of artificial intelligence, you've talked quite extensively and effectively to the impact in the near term, the positive impact of artificial intelligence, whether it's especially machine learning in medical applications, in education, and just making information more accessible, right? In the AI community, there is a kind of debate. So there's this shroud of uncertainty as we face this new world with artificial intelligence in it. And there's some people, like Elon Musk, you've disagreed on, at least on the degree of emphasis he places on the existential threat of AI. So I've spoken with Stuart Russell, Max Tegmark, who share Elon Musk's view, and Yoshio Bengio, Steven Pinker, who do not. And so there's a lot of very smart people who are thinking about this stuff, disagreeing, which is really healthy, of course. So what do you think is the healthiest way for the AI community to, and really for the general public to think about AI and the concern of the technology being mismanaged in some kind of way.
So the source of education for the general public has been robot killer movies,
right?
And Terminator, etc. And the one thing I can assure you we're not building are those kinds of solutions. Furthermore, if they were to show up, someone would notice and unplug them, right? So as exciting as those movies are, and they're great movies, were the killer robots to start, we would find a way to stop them, right? Yeah. So I'm not concerned about that. And much of this has to do with the time frame of conversation. Right. So you can imagine a situation 100 years from now when the human brain is fully understood and the next generation of brilliant MIT scientists have figured all this out. We're going to have a large number of ethics questions, right, around science and thinking and robots and computers and so forth and so on. So it depends on the question of the time frame. In the next 5 to 10 years, we're not facing those questions. What we're facing in the next 5 to 10 years is how do we spread this disruptive technology as broadly as possible to gain the maximum benefit of it. The primary benefits should be in healthcare and in education. Healthcare because it's obvious. We're all the same, even though we somehow believe we're not. As a medical matter, the fact that we have big data about our health will save lives, allow us to deal with skin cancer and other cancers, ophthalmological problems. There's people working on psychological diseases and so forth using these techniques. I can go on and on. The promise of AI in medicine is extraordinary. There are many, many companies and startups and funds and solutions, and we will all live much better for that. The same argument in education. Can you imagine that for each generation of child and even adult, you have a tutor educator that's AI-based, that's not a human but is properly trained, that helps you get smarter, helps you address your language difficulties or your math difficulties or what have you? Why don't we focus on those two? The gains societally of making humans smarter and healthier are enormous, right? And those translate for decades and decades, and we'll all benefit from them. There are people who are working on AI safety, which is the issue that you're describing. And there are conversations in the community that should there be such problems, what should the rules be like? Google, for example, has announced its policies with respect to AI safety, which I certainly support, and I think most everybody would support. And they make sense, right? So it helps guide the research. But the killer robots are not arriving this year, and they're not even being built.
And on that line of thinking, you said the time scale. In this topic or other topics, have you found it useful on the business side or the intellectual side to think beyond 5-10 years, to think 50 years out? Has it ever been useful or productive?
In our industry, there are essentially no examples of 50-year predictions that have been correct. Let's review AI, right? AI, which was largely invented here at MIT and a couple of other universities in the 1956, 1957, 1958. The original claims were a decade or two. And when I was a PhD student, I studied AI a bit, and it entered, during my looking at it, a period which is known as AI winter, which went on for about 30 years, which is a whole generation of scientists and a whole group of people who didn't make a lot of progress because the algorithms had not improved and the computers had not improved. It took some brilliant mathematicians, starting with a fellow named Jeff Hinton at Toronto and Montreal, who basically invented this deep learning model, which powers us today. The seminal work there was 20 years ago. And in the last 10 years, it's become popularized. So think about the time frames for that level of discovery. It's very hard to predict. Many people think that we'll be flying around in the equivalent of flying cars. Who knows? My own view, if I want to go out on a limb, is to say that when we know a couple of things about 50 years from now. We know that there'll be more people alive. We know that we'll have to have platforms that are more sustainable because the Earth is limited, in the ways we all know, and that the kind of platforms that are going to get built will be consistent with the principles that I've described. They will be much more empowering of individuals. They'll be much more sensitive to the ecology because they have to be. They just have to be. I also think that humans are going to be a great deal smarter. And I think they're going to be a lot smarter because of the tools that I've discussed with you. And of course, people will live longer. Life extension is continuing apace. A baby born today has a reasonable chance of living to 100, right? Which is pretty exciting. It's well past the 21st century, so we better take care of them.
And you mentioned an interesting statistic on some very large percentage, 60, 70% of people may live in cities.
Yeah. Today, more than half the world lives in cities. And one of the great stories of humanity in the last 20 years has been the rural to urban migration. This has occurred in the United States. It's occurred in Europe. It's occurring in Asia, and it's occurring in Africa. When people move to cities, the cities get more crowded, but believe it or not, their health gets better, their productivity gets better, their IQ and educational capabilities improve. So it's good news that people are moving to cities, but we have to make them livable and safe.
So you first of all, you are, but you've also worked with some of the greatest leaders in the history of tech. What insights do you draw from the difference in leadership styles of yourself, Steve Jobs, Elon Musk, Larry Page, now the new CEO, Sundar Pichai, and others, from the, I would say, calm sages to the mad geniuses?
One of the things that I learned as a young executive is that there's no single formula for leadership. They try to teach one, but that's not how it really works. There are people who just understand what they need to do and they need to do it quickly. Those people are often entrepreneurs. They just know and they move fast. There are other people who are systems thinkers and planners. That's more who I am. Somewhat more conservative, more thorough in execution, a little bit more risk averse. There's also people who are sort of slightly insane, right? In the sense that they are emphatic and charismatic and they feel it and they drive it and so forth. There's no single formula to success. There is one thing that unifies all of the people that you named, which is
yeah.
Let me ask you about this other world that of machine learning, of deep learning. What's your thoughts on the history and the current progress of machine learning field that's often progressed sort of separately as a space of ideas and space of people than the theoretical computer science or just even computer science world?
Yeah, it's really very different from the theoretical computer science world because the results about it, algorithmic performance tend to be empirical. It's more akin to the world of sat solvers, where we observe that for formulas arising in practice, the solver does well. So it's of that type. We're moving into the empirical evaluation of algorithms. Now, it's clear that there have been huge successes in image processing, robotics, natural language processing, a little less so, but across the spectrum of game playing is another one. There have been great successes. And one of those effects is that it's not too hard to become a millionaire if you can get a reputation in machine learning, and there'll be all kinds of companies that will be willing to offer you the moon because they think that if they have AI at their disposal, then they can solve all kinds of problems. But there are limitations. One is that the solutions that you get by supervised learning problems through convolutional neural networks seem to perform amazingly well, even for inputs that are outside the training set. But we don't have any theoretical understanding of why that's true. Secondly, the solutions, the networks that you get are very hard to understand, and so very little insight comes out. So, yeah, they may seem to work on your training set, and you may be able to discover whether your photos occur in a different sample of inputs or not. but we don't really know what's going on. We don't know the features that distinguish the photographs or the objects are not easy to characterize.
Well, it's interesting because you mentioned coming up with a small circuit to solve a particular size problem.
Yeah.
It seems that neural networks are kind of small circuits.
In a way, yeah.
But they're not programs. Sort of like the things you've designed are algorithms, programs.
Right.
Algorithms. Neural networks aren't able to develop algorithms to solve a problem. They are more of a function.
They are algorithms. It's just that they're...
but sort of, it could be a semantic question, but there's not a algorithmic style manipulation of the input. Perhaps you could argue there is.
Yeah, well...
It feels a lot more like a function of the input.
It's a function. It's a computable function. Once you have the network, you can simulate it on a given input and figure out the output. But what if you're trying to recognize images, then you don't know what features of the image are really being determinant of what the circuit is doing. The circuit is sort of very intricate, and it's not clear that the simple characteristics that you're looking for, the edges of the objects or whatever they may be, they're not emerging from the structure of the circuit.
Well, it's not clear to us humans, but it's clear to the circuit.
Yeah. Well, right.
I mean, it's not clear to sort of the elephant how the human brain works, but it's clear to us humans. We can explain to each other our reasoning, and that's why the cognitive science and psychology field exists. Maybe the whole thing of being explainable to humans is a little bit overrated.
Oh, maybe, yeah. I guess you could say the same thing about our brain, that when we perform acts of cognition, we have no idea how we do it, really.
Sure.
We do, though. I mean, we, at least for the visual system, the auditory system, and so on, we do get some understanding of the principles that they operate under. But for many deeper cognitive tasks, we don't have that.
That's right.
Specific.
So a crazy question, but I work a lot with machine learning, with deep learning. I'm not sure if you touch that world much, but you could think of programming as a thing that takes some input. A programming is the task of creating a program, and the program takes some input and produces some output. So machine learning systems train on data in order to be able to take an input and produce output. But they're messy, fuzzy things, much like we as children grow up. We take some input, we make some output, but we're noisy. We mess up a lot. We're definitely not reliable. Biological system are a giant mess. So there's a sense in which machine learning is a kind of way of programming, but just fuzzy. Mm-hmm. It's very, very, very different than C++. Because C++ is it's just like you said, it's extremely reliable, it's efficient, it's you can measure it, you can test it in a bunch of different ways. With biological systems or machine learning systems, you can't say much except sort of empirically saying that 99.8% of the time it seems to work. What do you think about this fuzzy kind of programming? And do you even see it as programming? Is it solely totally another kind of world?
I think it's a different kind of world. And it is fuzzy. And in my domain, I don't like fuzziness. That is, people say things like they want everybody to be able to program. But I don't want everybody to program my my airplane controls or the car controls. I want that to be done by engineers. I want that to be done with people that are specifically educated and trained for doing building things, and it is not for everybody. Similarly, a language like C++ is not for everybody. It is generated to be a sharp and effective tool for professionals, basically, and definitely for people who aim at some kind of precision. You don't have people doing calculations without understanding math, right? Counting on your fingers is not going to cut it if you want to fly to the moon. And so there are areas where an 84% accuracy rate, 16% false positive rate is perfectly acceptable, and where people will probably get no more than 70. You said 98%. What I have seen is more like 84, and by really a lot of blood, sweat, and tears, you can get up to the 92.5.
Right.
So this is fine if it is, say, pre-screening stuff before the human look at it. It is not good enough for life-threatening situations. And so there's lots of areas where the fuzziness is perfectly acceptable and good and better than humans, cheaper than humans, but it's not the kind of engineering stuff I'm mostly interested in. I worry a bit about machine learning in the context of cars. You know much more about this than I do.
I worry too.
But I'm sort of an amateur here. I've read some of the papers, but I've not ever done it. And the idea that scares me the most is the one I have heard, and I don't know how common it is, that you have this AI system, machine learning, all of these trained neural nets, and when there's something that's too complicated, they ask the human for help. But the human is reading a book or asleep, and he has 30 seconds or 3 seconds to figure out what the problem was that the AI system couldn't handle and do the right thing. This is scary. I mean, how do you do the cutover between the machine and the human?
It's very, very difficult. And for the designer of one of the most reliable, efficient, and powerful programming languages, C++, I can understand why that world is actually unappealing. It is for most engineers. To me, it's extremely appealing because we don't know how to get that interaction right, but I think it's possible. But it's very, very hard.
It is. I mean, I was stating a problem, not
that it's
solution.
Impossible.
I mean,
I would much rather never rely on a human. If you're driving a nuclear reactor, or an autonomous vehicle, it's much better to design systems written in C++ that never ask human for help.
Let's just get one fact in.
Yeah.
All of this AI stuff is on top of C++. So that's one reason I have to keep a weather eye out on what's going on in that field. But I will never become an expert in that area. But it's a good example of how you separate different areas of applications, and you have to have different tools, different principles, and they interact. No major system today is written in one language. And there are good reasons for that.
So there's an excitement about current machine learning methodologies. And there's really important good work you're doing in causal inference. Where is the future? Where do these worlds collide, and what does that look like?
First, they're going to work without collision. It's going to work in harmony.
Harmony. It's not collision.
The human is going to jumpstart the exercise by providing qualitative, non-committing models of how the universe works. How in the reality, the domain of discourse works. The machine is going to take over from that point of view and derive whatever the calculus says can be derived. namely quantitative answer to our questions.
Right.
These are complex questions. I'll give you some example of complex questions that will boggle your mind if you think about it. You take result of studies in diverse population under diverse conditions, and you infer the cause effect of a new population which doesn't even resemble any of the ones studied. And you do that by calculus. You do that by generalizing from one study to another. See what's common between the two. What is different? Let's ignore the differences and pull out the commonality. And you do it over maybe 100 hospitals around the world. From that, you can get really mileage from big data. It's not only you have many samples, you have many sources of data.
So that's a really powerful thing, I think, especially for medical applications. I mean, cure cancer, right? That's how from data you can cure cancer. Okay, let's look at machine learning. Machine learning today, if you look at deep neural networks, you can think of it as kind of conditional probability estimators.
Correct. Beautiful.
So
where did you say that?
What?
Conditional probability estimators. None of the machine learning people clobbered you? Attacked you?
Listen, most people, and this is why today's conversation I think is interesting, is most people would agree with you.
Yeah.
There's certain aspects that are just effective today, but we're going to hit a wall, and there's a lot of ideas. I think you're very right that we're going to have to return to about causality, and it would be let's try to explore it.
Okay.
Let's even take a step back. But the natural curiosity for me is that, yes, you're absolutely correct and important. And it's hard to believe that we haven't done this seriously, extensively already a long time ago. So this is really important work. But I also want to know, there's maybe you can philosophize about how hard is it to learn.
Okay, let's assume we're learning. We want to learn it, okay?
We want to learn.
So what do we do? We put a learning machine that watches execution trials in many countries and many locations, okay? Mm-hmm. All the machine can learn is to see shot or not shot, dead, not dead, court issued an order or didn't, okay? Just the facts. Mm-hmm. From the fact, you don't know who listens to whom. You don't know that the condemned person listen to the bullets, that the bullets are listening to the captain, okay? Mm-hmm. All we hear is one command, 2 shots, dead, okay? A triple of variables. Yes, no, yes, no. Okay. From that you can learn who listens to whom, and you can answer the question, no.
Definitively no. But don't you think you can start proposing ideas for humans to review?
You want machine to learn it, right? You want a robot. So a robot is watching trials like that, 200 trials, and then he has to answer the question, what if rifleman A refrained from shooting?
Yeah. So how do we do that?
That's exactly my point. That looking at the facts don't give you the strings behind the facts.
Absolutely. But do you think of machine learning as it's currently defined as only something that looks at the facts and tries
right now they only look at the facts. Yeah.
So is there a way to modify in your sense
playful manipulation?
Yes.
Doing
the interventionist kind of thing.
Yes.
Intervention.
But it could be at random. For instance, the rifleman is sick that day, or he just vomits or whatever. So a machine can observe this unexpected event which introduce noise. The noise still have to be random to be able to relate it to randomized experiment. And then you have observational studies from which to infer the strings behind the facts. Mm-hmm. It's doable to a certain extent. But now that we are expert in what you can do once you have a model, we can reason back and say what kind of data you need to build a model.
Got it. So, what role does machine learning play into that in that context of? You said, first of all, it's a beautiful shift. Anytime you shift your viewpoint into seeing that people are fundamentally good, and then you just have to verify and catch the ones who are not, as opposed to assuming everybody's bad. This is a beautiful thing. So what role does to you, throughout the history of the company, has machine learning played in doing that verification?
It was immediate. I mean, we weren't calling it machine learning, but it was data science. And then as the industry evolved, machine learning became more of the nomenclature, and as that evolved, it became more sophisticated with deep learning, and as that continues to evolve, it'll be another thing. But they're all in the same vein. But we built that discipline up within the first year of the company, because we also had, we had to partner with a bank, we had to partner with Visa, MasterCard, and we had to show that by bringing more people into the system, that we could do so in a responsible way that would not compromise their systems and that they would trust us.
How do you convince that this upstart company with some cool machine learning tricks is able to deliver on the sort of a trustworthy set of merchants?
We staged it out in tiers. We had a bucket of 500 people using it, and then we showed results, and then 1,000, and then 10,000, then 50,000, and then the constraint was lifted. So again, it's kind of getting something tangible out there. I want to show what we can do rather than talk about it, and that put a lot of pressure on us to do the right things. And it also created a culture of accountability, of a little bit more transparency, and I think incentivized all of our early folks and the company in the right way.
This ability to learn world models, I think, is the key to the possibility of learning machines that can also reason. So whenever I give a talk, I say there are three main challenges in machine learning. The first one is getting machines to learn to represent the world, and I'm proposing self-supervised learning. Mm-hmm. The second is getting machines to reason in ways that are compatible with essentially gradient-based learning, because this is what deep learning is all about, really. Mm-hmm. And the third one is something we have no idea how to solve, or at least I have no idea how to solve, is can we get machines to learn hierarchical representations of action plans? We know how to train them to learn hierarchical representations of perception, with convolutional nets and things like that, and transformers. But what about action plans? Can we get them to spontaneously learn good hierarchical representations of actions?
Also gradient based.
Yeah, all of that needs to be somewhat differentiable so that you can apply sort of gradient-based learning, which is really what deep learning is about.
So it's background knowledge, ability to reason in a way that's differentiable, that is somehow connected, deeply integrated with that background knowledge, or builds on top of that background knowledge, and then given that background knowledge, be able to make hierarchical plans in the world.
So if you take classical optimal control, there's something in classical optimal control called model predictive control. And it's been around since the early 60s. NASA uses that to compute trajectories of rockets. And the basic idea is that you have a predictive model of the rocket, let's say, or whatever system you intend to control, which, given the state of the system at time t, and given an action that you're taking on the system, so for a rocket it would be thrust and all the controls you can have, it gives you the state of the system at time t plus delta t, right? So basically a differential equation, something like that. And if you have this model, and you have this model in the form of some sort of neural net, or some sort of set of formula that you can backpropagate gradient through, you can do what's called model predictive control, or gradient-based model predictive control. So you have you can unroll that model in time. You feed it a hypothesized sequence of actions, and then you have some objective function that measures how well at the end of the trajectory the system has succeeded or matched what you wanted to do. Is it a robot arm? Have you grasped the object you want to grasp? If it's a rocket, are you at the right place near the space station? Things like that. And by backpropagation through time, and again, this was invented in the 1960s by optimal control theorists, you can figure out what is the optimal sequence of actions that will, get my system to the best final state. So that's a form of reasoning. It's basically planning, and a lot of planning systems in robotics are actually based on this. And you can think of this as a form of reasoning. So, to take the example of the teenager driving a car again, you have a pretty good dynamical model of the car. It doesn't need to be very accurate, but again, that if you turn the wheel to the right and there is a cliff, you're going to run off the cliff, right? You don't need to have a very accurate model to predict that. And you can run this in your mind and decide not to do it for that reason, because you can predict in advance that the result is going to be bad. So you can sort of imagine different scenarios and then, employ or take the first step in the scenario that is most favorable, and then repeat the process of planning. That's called receding horizon model predictive control. Mm-hmm. So even all those things have names, going back decades. And so if you're not in classical optimal control, the model of the world is not generally learned. There's sometimes a few parameters you have to identify. That's called systems identification. But generally, the model is mostly deterministic and mostly built by hand. So the big question of AI, I think the big challenge of AI for the next decade is how do we get machines to learn predictive models of the world that deal with uncertainty and deal with the real world in all this complexity. So it's not just the trajectory of a rocket, which you can reduce to first principles. It's not even just the trajectory of a robot arm, which again, you can model by, careful mathematics, but it's everything else, everything we observe in the world, people, behavior, physical systems that involve collective phenomena like water or trees and, branches in a tree or something, or like complex things that, humans have no trouble developing abstract representations and predictive model for, but we still don't know how to do with machines.
Where do you put in these three, maybe in the planning stages, the game theoretic nature of this world, where your actions not only respond to the dynamic nature of the world, the environment, but also affect it? So if there's other humans involved, is this point number 4, or is it somehow integrated into the hierarchical representation of action in your view?
I think it's integrated. It's just that now your model of the world has to deal with, it just makes it more complicated, right? The fact that humans are complicated and not easily predictable, that makes your model of the world much more complicated, that much more complicated.
Well, there's the focus in your book and algorithmic fairness research today in general is on machine learning, like we said, is data. And just even the entire AI field right now is captivated with machine learning, with deep learning. Do you think ideas in symbolic AI or totally other kinds of approaches are interesting, useful in the space, have some promising ideas in terms of fairness?
I haven't thought about that question specifically in the context of fairness. I definitely would agree with that statement in the large, right? I mean, I am, one of many machine learning researchers who do believe that the great successes that have been shown in machine learning recently are great successes, but they're on a pretty narrow set of tasks. I mean, yes. I don't think we're kind of notably closer to general artificial intelligence now than we were when I started my career. I mean, there's been progress. And I do think that we are kind of as a community maybe looking a bit where the light is, but the light is shining pretty bright there right now, and we're finding a lot of stuff. So I don't want to argue with the progress that's been made in areas like deep learning, for example. And I think within the field of algorithmic game theory, perhaps the single most important kind of technical contribution that's been made is the realization between close connections between machine learning and game theory, and in particular between game theory and the branch of machine learning that's known as no regret learning. And this sort of provides a very general framework in which a bunch of players interacting in a game or a system, each one kind of doing something that's in their self-interest, will actually kind of reach an equilibrium, and actually reach an equilibrium in a pretty, a rather short amount of steps.
So you kind of mentioned acting greedily can somehow end up pretty good for everybody.
Or pretty bad.
Or pretty bad.
Yeah.
It'll end up stable.
Yeah, right. and stability or equilibrium by itself is not necessarily either a good thing or a bad thing.
So what's the connection between machine learning and the ideas?
Well, I think we've kind of talked about these ideas already in kind of a non-technical way, which is maybe the more interesting way of understanding them first, which is, we have many systems, platforms, and apps these days that work really hard to use our data and the data of everybody else on the platform to selfishly optimize on behalf of each user. Okay. So, let me give, I think, the cleanest example, which is just driving apps, navigation apps like, Google Maps and Waze, where, miraculously compared to when I was growing up, at least, the objective would be the same when you wanted to drive from point A to point B, spend the least time driving, not necessarily minimize the distance, but minimize the time, right? And when I was growing up, like the only resources you had to do that were like maps in the car, which literally just told you what roads were available. And then you might have like half-hourly traffic reports just about the major freeways, but not about side roads. So you were pretty much on your own. And now we've got these apps. You pull it out and you say, I want to go from point A to point B. And in response kind of to what everybody else is doing, if you like, what all the other players in this game are doing right now, here's the route that minimizes your driving time. So it is really kind of computing a selfish best response for each of us in response to what all of the rest of us are doing at any given moment. And so, I think it's quite fair to think of these apps as driving or nudging us all towards the competitive or Nash equilibrium of that game. Now, you might ask, like, well, that sounds great. Why is that a bad thing? Well, it's known both in theory and with some limited studies from actual like traffic data that all of us being in this competitive equilibrium might cause our collective driving time to be higher, maybe significantly higher than it would be under other solutions. And then you have to talk about what those other solutions might be and what the algorithms to implement them are, which we do discuss in the kind of game theory chapter of the book. But similarly, on social media platforms or on Amazon, all these algorithms that are essentially trying to optimize our behalf, they're driving us in a colloquial sense towards some kind of competitive equilibrium. And, one of the most important lessons of game theory is that just because we're at equilibrium doesn't mean that there's not a solution in which some or maybe even all of us might be better off. Mm-hmm. And then the connection to machine learning, of course, is that in all these platforms I've mentioned, the optimization that they're doing on our behalf is driven by machine learning. Like predicting where the traffic will be, predicting what products I'm going to like, predicting what would make me happy in my news feed.
So from the perspective, you've done obviously a lot of incredible work in machine learning. So what role do you think data and machine learning play in this goal of trying to understand diseases and trying to eradicate diseases?
Up until now, I don't think it's played very much of a significant role, because largely the data sets that one really needed to enable a powerful machine learning methods, those data sets haven't really existed. There's been dribs and drabs and some interesting machine learning that has been applied, I would say machine learning / data science. But the last few years are starting to change that. So we now see an increase in some large data sets, but equally importantly, an increase in technologies that are able to produce data at scale. It's not typically the case that people have deliberately, proactively used those tools for the purpose of generating data for machine learning. They to the extent that those techniques have been used for data production. They've been used for data production to drive scientific discovery, and the machine learning came as a sort of byproduct second stage of, now we have a data set, let's do machine learning on that rather than a more simplistic data analysis method. But what we are doing at In Sitro is actually flipping that around and saying, here's this incredible repertoire of methods that bioengineers, cell biologists have come up with. Let's see if we can put them together in brand new ways with the goal of creating data sets that machine learning can really be applied on productively to create powerful predictive models that can help us address fundamental problems in human health.
So really focus to make data the primary focus and the primary goal, and use the mechanisms of biology and chemistry to create the kinds of data set that could allow machine learning to benefit the most.
I wouldn't put it in those terms, because that says that data is the end goal. Data is the means. So for us, the end goal is helping address challenges in human health. And the method that we've elected to do that is to apply machine learning to build predictive models. And machine learning, in my opinion, can only be really successfully applied, especially the more powerful models, if you give it data that is of sufficient scale and sufficient quality. So how do you create those data sets so as to drive the ability to generate predictive models which subsequently help improve?
Or run a red light.
So it sounds like already for Waymo, like machine learning is a huge part of the stack. So it's a huge part of not just, so obviously the first level 0 or whatever you said, which is like just the object detection of things that, that machine learning can do, but also starting to do prediction of behavior and so on, to model the other parties in the scene, entities in the scene are going to do. So machine learning is more and more playing a role in that as well.
Of course. Absolutely. I think we've been going back to the earliest days, like DARPA, even the DARPA Grand Challenge. Our team was leveraging machine learning. It was like ImageNet, and it was a very different type of ML. But and I think actually it was before my time. But the Stanford team during the Grand Challenge had a very interesting machine learned system that would use LiDAR and camera. We've been driving in the desert, and we had built the model where it would kind of extend the range of free space reasoning. So we get a clear signal from LiDAR, and then it had a model that said, hey, like this stuff in camera kind of sort of looks like this stuff in LiDAR, and I know this stuff that I'm seeing in LiDAR, I'm very confident it's free space, so let me extend that free space zone into the camera range that would allow the vehicle to drive faster. Right? And then we've been building on top of that and kind of staying and pushing the state of the art in ML, in all kinds of different ML over the years. And in fact, from the earliest days, I think 2010 is probably the year where Google, maybe 2011 probably, got pretty heavily involved in machine learning, kind of deep nets. And at that time, it was probably the only company that was very heavily investing in kind of state-of-the-art ML and self-driving cars, right? And they go hand in hand. And we've been on that journey ever since. We're pushing a lot of these areas in terms of research, at Waymo, and we collaborate very heavily with the researchers in Alphabet, and like all kinds of ML, supervised ML, unsupervised ML. We've published some interesting research papers in the space, especially recently. It's just super active
learning as well.
Yeah, so super active. And of course, there's kind of like more mature stuff, like ConvNets for object detection, but there's some really interesting, really active work that's happening in kind of more and bigger models, and models that have more structure to them, not just large bitmaps, and reason about temporal sequences. And some of the interesting breakthroughs that we've seen in language models, right? Transformers, GPT-3 and friends. There's some really interesting applications of some of the core breakthroughs to those problems of behavior prediction, as well as decision making and planning. Right? You can think about it, kind of the behavior, how the path, the trajectories, the how people drive. They have kind of share a lot of the fundamental structure. This problem, there's sequential nature. There's a lot of structure in this representation. There is a strong locality, kind of like in sentences, words that follow each other, they're strongly connected, but there's also kind of larger context that doesn't have that locality. And you also see that in driving, right? What, is happening in the scene as a whole has very strong implications on, the kind of the next step in that sequence whether you're, predicting what other people are going to do, whether you're making your own decisions, or whether in the simulator, you're building generative models of, humans walking, cyclists riding, and other cars driving.
Oh, that's all really fascinating. Like how it's fascinating to think that transformer models and all the breakthroughs in language and NLP that might be applicable to like driving at the higher level, at the behavioral level. That's kind of fascinating. In terms of artificial intelligence, nobody really knows what are the limits of our current approaches. You mentioned machine learning.
Yeah.
How do we create human level intelligence? It seems that there's a lot of very smart physicists who perhaps oversimplify the nature of intelligence and think of it as information processing. And therefore, there doesn't seem to be any theoretical reason why we can't artificially create human level or superhuman level intelligence. In fact, the reasoning goes, if you create human level intelligence, the same approach you just used to create human level intelligence should allow you to create superhuman level intelligence very easily, exponentially. So what do you think that way of thinking that comes from physicists is all about?
I wish I knew, but there's a particular reason why I wish I knew. I have a second job. I consult for Google. Not for Google, for Google X. I am the senior academic advisor to a group of machine learning physicists. Now, that sounds crazy because I know nothing about the subject. I know very little about the subject. On the other hand, I'm good at giving advice, so I give them advice on things. Anyway, I see these young physicists who are approaching the machine learning problem. There is a real machine learning problem, namely, why does it work as well as it does? Right. Nobody really seems to understand why it is capable of doing the kind of generalizations that it does and so forth. And there are three groups of people who have thought about this. There are the engineers. The engineers are incredibly smart, but they tend not to think as hard about why the thing is working as much as they do how to use it. Obviously, they've provided a lot of data, and it is they who demonstrated that machine learning can work much better than you had any right to expect. The machine learning systems are systems. The system's not too different than the kind of systems that physicists study. There's not all that much difference between quantum in the structure of the mathematics. Physically, yes, but in the structure of the mathematics, between a tensor network designed to describe a quantum system on the one hand, and the kind of networks that are used in machine learning. So there more and more, I think, young physicists are being drawn to this field of machine learning. Some very, very good ones. I work with a number of very good ones, not on machine learning, but on having lunch.
On having lunch?
Right.
Yeah.
And I can tell you they are super smart.
Yes.
They don't seem to be so arrogant about their physics backgrounds that they think they can do things that nobody else can do. But the physics way of thinking, I think, will add great value to, or will bring value to the machine learning. I believe it will. And I think it already has.
You've mentioned machine learning reinforcement quite a bit. I mean, to me, social networks is one of the exciting places, recommender systems where machine learning is applied. Where else in the world, in the space of possibilities over the next 5, 10, 20 years, do you think we're going to see impact of machine learning? When you try it on a philosophical level, on a technical level, what do you think? Or within social networks themselves?
Well, I think the obvious answers are climate change, right? Like, think about how much fuel or just waste there is in energy consumption today because we don't plan accordingly, because we take the least efficient route, or
the logistics and stuff, the supply chain, all that kind of stuff.
Yeah, I mean, listen, if we're gonna fight climate change, like one awesome way to do it is figure out how to optimize how we operate as a species and and minimize the amount of energy we consume to maximize whatever economic impact we want to have. Because right now, those two are very much tied together. And I don't believe that has to be the case. There's this really interesting, you've read it. For people who are listening, there's this really interesting paper on reinforcement learning and energy consumption inside buildings. It's like one of the seminal ones, right? But imagine that at massive scale. That's super interesting. I mean, they've done like resource planning for servers for peak load using reinforcement learning. I don't know if that was at Google or somewhere else, but like, okay, great, you do it for servers, but what if you could do it for just capacity and general energy capacity for cities and planning for traffic? And of course, there's all the self-driving cars, and I don't know, like I'm not going to pontificate like crazy ideas using reinforcement learning or machine learning. It's just so clear to me that humans don't think quickly enough.
So it's interesting to think about machine learning helping a little bit at scale. So a little bit to a large number of people, that has a huge impact. So if you optimize, it's like Google Maps, something like that, trajectory planning, or what is MapQuest first.
Getting here, I looked and it was like, here's the most energy efficient route. And I was like, I'm going to be late. I need to take the fastest route.
As opposed to unrolling the map.
Yeah.
And then that's going to be very inefficient no matter what.
I was definitely the other day, like part of the Epsilon Greedy with Waze, where like I was sent on like a weird route that I could tell they're like, we just need to collect data of this road. Like we just, Kevin's
You're the ant they sent off for
Kevin's
exploration.
definitely going to be the guinea pig. And great. Now we have.
Did you at least feel pride?
Oh, going through it, I was like, oh, this is fun. Like now they get data about this weird shortcut. And actually I hit all the green lights and it worked. I'm like, this is a problem.
This is bad data.
Bad data. They're just going to imagine.
I could see you slowing down and stopping at a green light just to give them the right kind of data.
Yep. But to answer your question, like I feel like that was fairly unsatisfying, and it's easy to say climate change. But what I would say is, at Instagram, everything we applied machine learning to got better for users, and it got better for the company. And I saw the power. I didn't fully understand it as an executive, and I think that's actually one of the issues that. And when I say understand, I mean the mathematics of it. Like I understand what it does. I understand that it helps. But there are a lot of executives now that talk about it in the way that they talk about the internet, or they talked about the internet like 10 years ago. They're like, we're going to build mobile. And you're like, what does that mean? They're like, we're just going to do mobile. And you're like, okay. So my sense is the next generation of leaders will have grown up having had classes in reinforcement learning, supervised learning, whatever. And they will be able to thoughtfully apply it to their companies in the places it is needed most. And that's really cool. Because I mean, talk about efficiency gains. That's what excites me the most about it.
Yeah, so it's interesting just to get a fundamental first principles understanding of certain concepts of machine learning. So supervised learning from an executive perspective. Supervised learning, you have to have a lot of humans label a lot of data. So the question there is, okay, can we gather a large amount of data that can be labeled well? And that's the question Tesla asked, like, can we create a data engine that keeps sending an imperfect machine learning system out there? Whenever it fails, it gives us data back. We label it by human and we send it back and forth this way. Then there is Yann LeCun's excited about this self-supervised learning, where you do much less human labeling, and there's some kind of mechanism for the system to learn it by itself on the human generated data. And then there's the reinforcement learning, which is like basically allowing it's applying the AlphaZero technology that allow through self-play to learn how to solve the game of Go and achieve incredible levels at the game of chess. Can you formulate the problem you're trying to solve in a way that's amenable to reinforcement learning? And can you get the right kind of signal at scale? Because you need a lot of signal. And that's kind of fascinating to see which part of a social network can you convert into a reinforcement learning problem.
The fascinating thing about reinforcement learning, I think, is that we now have learned to apply neural networks to guess, like the Q function, basically the values for any state in action. And that is fascinating because we used to just like I don't know, have like a linear regression, like hope it worked. And that was the fanciest version of it. But now you look at it, I'm like trying to learn this stuff. And I look at it, I'm like, there are like 17 different acronyms of different ways you can try to apply this. No one quite agrees, like, what's the best? Generally, if you're trying to like build a neural network, there are pretty well-trodden ways of doing that. You use Atom, you use ReLU, you use, like, there's just like general good ideas. And in reinforcement learning, I feel like the consensus is like, it totally depends. And by the way, it's really hard to get it to converge, and it's noisy, and it like, so there are all these really interesting ideas around building simulators. You know, like for instance, in self-driving, right? Like you don't want to like actually have someone get in an accident to learn that an accident is bad. So you start simulating accidents, simulating aggressive drivers, or simulating crazy dogs that run into the street. And wow, fascinating, right? Like my mind starts racing. And then the question is, okay, forget about self-driving cars. Let's talk about social networks. How can you produce a better, more thoughtful experience using these types of algorithms? And honestly, in talking to some of the people that work at Facebook and old Instagrammers, most people are like, yeah, we tried a lot of things, didn't quite ever make it work. I mean, for the longest time, Facebook ads was effectively a logistic regression. Okay. I don't know what it is now, but like, if you look at this paper that they published back in the day, it was literally just a logistic regression. Made a lot of money. So even at these like extremely large scales, if we are not yet touching what reinforcement learning can truly do, imagine what the next 10 years looks like.
Yeah.
How cool is that?
It's amazing. So I really like the use of reinforcement learning as part of the simulation. For example, like with self-driving cars, it's modeling pedestrians. So the nice thing about reinforcement learning, it can be used to learn agents within the world. So they can learn to behave properly. Like you can teach pedestrians to, like, you don't hard code the way they behave. They learn how to behave. In that same way, I do have a hope. What is it? Jack Dorsey talks about healthy conversations. You talked about meaningful interactions, I believe.
Yeah.
Like simulating interactions so you can learn how to manage that is fascinating. So where most of your algorithm development happens in virtual worlds. And then you can really learn how to design the interface, how you design a bunch of aspects of the experience in terms of how you select what's shown in the feed, all those kinds of things. That it feels like if you can connect reinforcement learning to that, that's super exciting.
Yep. And I think if you have a company and leadership that believe in doing the right things and can apply this technology in the right way, some really special stuff can happen. Yeah. It is mostly likely going to be a group of people we've never heard about, who start up from scratch, right? And you asked if like new social networks could be built. I've got to imagine they will be. And whoever starts it might be some kids in a garage that took these classes from these people, right? Like, and they're building all of these things with this tech at the core. So I'm trying not to be someone who just like throws around reinforcement learning as a buzzword. I truly believe that it is the most cutting edge in what can happen in social networks. And I also believe it's super hard. Like it's super hard to make it work. It's super hard to do it at scale. It's super hard to find people that truly understand it. So I'm not going to say that like, I think it'll be applied in social networks before we have true self-driving.
Yeah.
Let me put it that way.
We could argue about this for a long time, but yes, I agree with you. So I think self-driving is way harder than people realize.
Oh, absolutely.
So how much of this is a machine learning problem? What role does ML, machine learning, play in this whole problem of autonomous driving, autonomous trucking?
Mm-hmm. It's massive, and it's increasing over time. If you go back to the grand challenge days in the early days of kind of AV development, there was ML, but it was not in like kind of the mass scale data style of ML. It was like learning models, but in a more structured kind of way. And it was a lot of heuristic and search-based approaches and planning and so forth. You can make a lot of progress with these types of approaches kind of across the board, an almost deceptive amount of progress. We can get pretty far, but then you start to really grind the further you get in some parts of the stack if you don't have an ability to absorb a massive amount of experience in a way that scales very sublinearly in terms of human labor and human attention. And so when you look at the stack, the perception side is probably the first to get really revolutionized by ML, and it goes back many years because ML for like computer vision and these types of approaches kind of took off, was a lot of the like early kind of push in deep learning. And so there's always a debate on, the spectrum between kind of like end-to-end ML, which, is a little bit kind of like too far, to how you architect it to where you have modules, but enough ability to think about long tail problems and so forth. But at the end of the day, you have big parts of the system that are very ML and data driven. And we're increasingly moving in that direction all the way across the board, including behavior, where even when it's not like a gigantic ML problem that covers like a giant swath end to end, more and more parts of the system have this property where you want to be able to put more data into it, and it gets better. And that has been one of the realizations as you drive tens of millions of miles and try to like solve new expansions of domains without regressing in your old ones. It becomes intractable for a human to approach that in the way that traditionally robotics has kind of approached some elements of the tech stack.
So are you trying to create a data pipeline specifically for the trucking problem? Is it like how much leveraging of the autonomous driving is there in terms of data collection?
Yeah.
And how unique is the data required for the trucking problem?
So we reuse all the same infrastructure. So labeling workflows, ML workflows, everything. So that actually carries over quite well. We heavily reuse the data even, where almost every model that we have on a truck, we started with the latest car model.
Cool.
And
so it's almost like a good background model.
Yeah, it's like you can think of like, despite the different domain and different numbers of sensors and position of sensors, there's a lot of signals that carry over across driving. And so it's almost like pre-training and getting a big boost out of the gate where you can reduce the amount of data you need by a lot. And it goes both ways, actually. And so we're increasingly thinking about our data strategy on how we leverage both of these. So you think about how other agents react to a truck. Yeah, it's a little bit different, but the fundamentals are actually like, what will other vehicles in the road do? There's a lot of carryover that's possible. And in fact, just to give you an example, we're constantly kind of like adding more data from the trucking side. But as of right now, when we think of one of our models, behavior prediction for other agents on the road, like vehicles, 85% of that data comes from cars. And a lot of that 85% comes from surface streets because we just had so much of it and it was really valuable. And so we're adding in more and more, particularly in the areas where we need more data, but you get a huge boost out of the gate.
Just all different visual characteristics of roads, lane markings, pedestrians, all that's still relevant.
It's all still relevant. And then just the fundamentals of how, you detect the car. Does it really change that much, whether you're detecting it from a car or a truck? The fundamentals of how a person will walk around your vehicle, it'll change a little bit, but the basics, like there's a lot of signal in there that as a starting point to a network can actually be very valuable. Now, we do have some very unique challenges where there's a sparsity of events on a freeway. The frequency of events happening on a freeway, whether it's, interesting objects in the road or incidents or even like from a human benchmark, like how often does a human have an accident on a freeway, is far more sparse than on a surface street. And so that leads to really interesting data problems where you can't just drive infinitely to encounter all the different permutations of things you might encounter. And so there you get into interesting tools like structured testing and data collection, data augmentation, and so forth. And so there's really interesting kind of technical challenges that push some of the research that enables these new suites of approaches.
What role does simulation play?
Really good question. So Waymo simulates about 1,000 miles for every mile it drives. So you think of
across the board.
Across the board, yeah. So you think of, for example, if we've driven over 20 million miles, that's over 20 billion miles in simulation. Wow. Now, how do you use simulation? It's multi-purpose. So you use it for basic development. So you want to make sure you have regression prevention and protection of everything you're doing, right? That's an easy one. when you encounter something interesting in the world, let's say there was an issue with how the vehicle behaved versus an ideal human, you can play that back in simulation and start augmenting your system and seeing how you would have reacted to that scenario with this improvement or this new area. You can create scenarios that become part of your regression set after that point, right? Then you start getting into like really, really like kind of hill climbing where you say, hey, I need to improve this system. I have these metrics that are really correlated with final performance. How do I know how well I'm doing? The actual physical driving is the least efficient form of testing, and it's expensive, it's time consuming. So grabbing a large scale batch of historical data and simulating it to get a signal of over these last, or just random sample of 100,000 miles, how has this metric changed versus where we are today? You can do that far more efficiently in simulation than just driving with that new system on board, right? And then you go all the way to the validation phase where to actually see your human relative safety of like how well are you performing on the car side or the trucking side relative to a human. A lot of that safety case is actually driven by taking all of the physical operational driving, which probably includes a lot of interventions where the driver took over just in case. And then you simulate those forward and see if would anything have happened. And in most cases, the answer is no, but you can simulate it forward. And you can even start to do really interesting things where you add virtual agents to create harder environments. You can fuzz the locations of physical agents. You can muck with the scene and stress test the scenario from a whole bunch of different dimensions. And effectively, you're trying to like more efficiently sample this like infinite dimensional space, but try to encounter the problems as fast as possible. Because what most people don't realize is the hardest problem in autonomous driving is actually the evaluation problem in many ways, not the actual autonomy problem. And so if you could, in theory, evaluate perfectly and instantaneously, you can solve that problem in a really fast feedback loop quite well. But the hardest part is being really smart about this suite of approaches on how can you get an accurate signal on how well you're doing as quickly as possible in a way that correlates to physical driving.
Can you explain the evaluation problem? Which metric are you evaluating towards? Are we talking about safety or what are the performance metrics that we're talking about?
So in the end, you care about end safety. Like that's in the end what keeps you that's what's deceptive where there's a lot of companies that have like a great demo. The path from like a really great demo to being able to go driverless can be deceptively long, even when that demo looks like it's driverless quality. And the difference is that the thing that keeps you from going driverless is not the stuff you encounter on a demo. It's the stuff that you encounter once in 100,000 miles or 500,000 miles. Yeah. And so that is at the root of what is most challenging about going driverless, because any issue you encounter, you can go and fix it. But how do you know you didn't create 5 other issues that you haven't then encountered yet? So those learnings, like those were painful learnings in Waymo's history that Waymo went through and led to us then finally being able to go driverless in Phoenix, and now are at the heart of how we develop. Evaluation is simultaneously evaluating final kind of end safety of how ready are you to go driverless, which may be as direct as what is your collision, human relative kind of collision rate for all these types of scenarios and severities to make sure that you're better than a human bar, by a good amount. But that's not actually the most useful for development. For development, it's much more kind of analog metrics that are part of the art of finding what are the properties of driving that give you a way quicker signal that's more sensitive than a collision, that can correlate to the quality you care about and push the feedback loop to all of your development. A lot of these are, for example, comparisons to human drivers, like manual drivers. And how do you do relative to a human driver in various dimensions or various circumstances?
Can I ask you a tricky question? So if I brought you a truck, how would you test it? Okay, Alan Turing came along and you said...
This one's can't tell if it's a human driver or autonomous driver. Yeah,
but not the human because humans are flawed.
It's different, but how do you actually know you're ready, basically? And how do you know it's good enough? And by the way, this is the reason why Waymo released a safety framework for the car side, because one, it sets the bar so nobody cuts below it and does something bad for the field that causes an accident. 2, it's to start the conversation on framing what does this need to look like. Same thing we'll end up doing for the trucking side. It ends up being different portfolio of approaches. There's easy things like, are you compliant with all these like fundamental rules of the road? Like you never drive above the speed limit. That's actually pretty easy. Like you can fundamentally prove that it's either impossible to violate that rule, or that in these like, you can itemize the scenarios where that comes up, and you can do a test and show that you pass that test, and therefore you can handle that scenario. Mm-hmm. And so those are like traditional structured testing kind of system engineering approaches where you can just fault rates is another example where when something fails, how do you deal with it? You're not going to drive and randomly wait for it to fail. You're going to force a failure and make sure that you can handle it in closed courses and simulation or on the road, and run through all the permutations of failures, which you can oftentimes, for some parts of the system, itemize, like hardware. Mm-hmm. The hardest part is behavioral, where you have just infinite situations that could, in theory, happen, and you want to figure out the combinations of approaches that can work there. You can probably pass the Turing test pretty quickly, even if you're not like completely ready for driverless, because the events that are really kind of like hard will not happen that often. Just to give you a perspective, a human has a serious accident on a freeway. Like a truck driver on a freeway has, there's a serious event happens once every 1.3 million miles. Mm-hmm. And something that actually has like a really serious injury is 28 million miles. And so those are really rare. And so you could have a driver that looks like it's ready to go, but you have no signal on what happens there. And so that's where you start to get creative on combinations of sampling and statistical arguments, focused structured arguments where you can kind of simulate those scenarios and show that you can handle them, and metrics that are correlated with what you care about, but you can measure much more quickly and get to a right answer. Mm-hmm. And that's what makes it pretty hard. And in the end, you end up borrowing a lot of properties from aerospace and like space shuttles and so forth, where you don't get the chance to launch it a million times just to say you're ready because it's too expensive to fail. And so you go through a huge amount of kind of structured approaches in order to validate it. And then by thoroughness, you can make a strong argument that you're ready to go. This is actually a harder problem in a lot of ways, though, because you can think of a space shuttle as getting to a fixed point, and then you kind of like, or an airplane, and you like freeze the software and then you like prove it and you're good to go. Here you have to get to a driverless quality bar, but then continue to aggressively change the software even while you're driverless. And so,
and also the full range of environment that there's an external environment with a shuttle. You're basically testing the systems, the internal stuff.
Yeah.
And you have a lot of control in the external stuff.
Yeah. And the hard part is, how do you know you didn't get worse in something that you just changed?
Yes, sure.
And so in a lot of ways, like the Turing test starts to fail pretty quickly because you start to feel driverless quality pretty early in that curve. If you think about it, right, like in most kind of really good AV demos, maybe you'll sit there for 30 minutes, right?
Yeah.
So you've driven 15 miles or something like that. To go driverless, like what's the sort of rate of issues that you need to have you won't even encounter?
So let's try something different then. Let's try a different version of the Turing test, which is like an IQ test. Uh-huh. So there's these difficult questions of increasing difficulty. They're designed, you don't know them ahead of time. Nobody knows the answer to them.
Right.
And so is it possible to, in the future, orchestrate basically really
obstacle course almost of like
that maybe change every year, and that represent, if you can pass these, they don't necessarily represent the full spectrum.
That's it. Yeah, they won't be conclusive, but you can at least get a really quick read and filter.
Yeah, like you're able to, because you didn't know them ahead of time. Like, I don't know, probably
like construction zones, failures,
or driving anywhere in Russia.
Yeah, exactly.
Snow,
weather, cut-ins, dense traffic, kind of merging, lane closures, animal foreign objects on a road that pop out on short notice, mechanical failures, sensor breaking, tire popped, weird behaviors by other vehicles, like a hard brake, something reckless that they've done. Fouling of sensors like bugs or birds, poop or something. So, but you have these like kind of like extreme conditions where like you have a nasty construction zone where everything shuts down and you have to like go, get pulled to the other side of the freeway with a temporary lane like that. Right? Those are sort of conditions where we do that to ourselves, right? We itemize everything that could possibly happen to give you a starting point to how to think about what you need to develop. And at the end of the day, there's no substitute for real miles. Like if you think of traditional ML, like, you know how there's like a validation set where you hold out some data, and like real world driving is the ultimate validation set. That's in the end, like the cleanest signal. But you can do a really good job on creating an obstacle course. And you're absolutely right. Like at the end, if there was such a thing as automating and kind of a readiness, it would be these extreme conditions, like a red light runner, right? A really reckless pedestrian that's jaywalking, a cyclist that, you know, makes like a really awkward maneuver. That's actually what keeps you from going driverless. Like in the end, that is the long tail.
Yeah, and it's interesting to think about that. To me is the Turing test. Turing test means a lot of things, but to me in driving, the Turing test is exactly this validation set that is handcrafted. There's I don't know if you know him. There's a guy named Francois Cholet. He thinks about like how to design a test for general intelligence. He designs these IQ tests for machines, and the validation set for him is handcrafted.
Yeah.
And that it requires like human genius or ingenuity to create a really good test.
Yeah.
And you truly hold it out. It's an interesting perspective on the validation set, which is like, make that as hard as possible.
Right.
Not a generic representation of the data, but this is the hardest.
The hardest
thing.
stuff. Yeah. You know, it's like Go. Like you'll never fully itemize like all the world states that you'll expand. And so you have to come up with different approaches. And this is where you start hitting the struggles of ML, where ML is fantastic at optimizing the average case. It's a really unique craft to think about how you deal with the worst case, which is what we care about in the AV space, when using an ML system on something that occurs like super infrequently. So like you don't care about the worst case really on ads, because if you miss a few, it's not a big deal, but you do care about it on the driving side. And so typically like you'll never fully enumerate the world. And so you have to take a step back and abstract away what are the signals that you care about and the properties of a driver that correlate to defensive driving and avoiding nasty situations that even though you'll always be surprised by things you'll encounter, you feel good about your ability to generalize from what you've learned.
All right, let me ask you a tricky question. So to me,